2, 1.
Good morning, everyone. My name is Alat Kamil, and I will be serving as the designated federal official to the U.S. EPA Science Advisory Committee on Chemicals, which we call SAC. For this meeting and in my role, I will be opening this public meeting, and I want to thank Dr. George Cobb for agreeing to serve as chair of the committee for this meeting. I also want to thank the members of the committee, the ad hoc reviewers, and the public for attending this important meeting. We appreciate the time and effort of the committee members in preparing for this meeting, taking into account their busy schedules. I would like to seize this opportunity and welcome our new SAC members. The new members are Dr. Stephanie Ike, Dr. Mary Fox, Dr. Cynthia Graham, Dr. Allison Jenkins, Dr. Francesca Merced-Neves, Dr. Mary Oettinger, Dr. Rainbow Rubin, Dr. Mark Rumpler, and Dr. Michael Wright. We are confident we will be adding to the expertise of the committee, and we wish you success in this and the following meetings. In addition, I want to thank EPA's Office of Pollution Prevention and Toxics, which we call OPPT, and my colleagues at the Peer Review and the Ethics Branch in EPA for their hard work in preparing for this important review of EPA's 2023 draft supplement to the 1,4-dioxane risk evaluation. I would also like to thank my colleagues, Steve Knott, the Chief of the Peer Review of Ethics Branch, Mission Support Division of the Office of Program Support, and Tamu Gibson, the Executive Secretary of the FIFRA Scientific Advisory Panel and the Science Advisory Committee on Chemicals. They are both online this week and will serve as backups to my role as designated federal official, or DFO. Thanks are also due to Dr. Charlene Matten and William Woogie, our Assistant Deputy Ethics Officials, who are also DFOs, and to Ms. Joyce Coates and Ms. Barbara Ewell, and our contractor, Kurd Ali from Indina, who provided administrative support. The SAC is a federal advisory committee that provides independent scientific peer review and advice to the EPA on the chemical-related issues regarding the impact of proposed regulatory actions on human health and the environment. The SAC provides advice and recommendations to the EPA. Decision-making and implementation authority remains with the agency. The SAC for this meeting is comprised of 18 members who are experts in toxicology, environmental risk assessment, exposure assessment, and related scientists. The expertise of these members is augmented by 10 ad hoc reviewers who are temporary participants in the SAC activities, providing additional scientific expertise, including environmental exposure release from industrial sources for review of Monte Carlo release assessment methods, evaluating the application of occupational exposure modeling approaches and monitoring data for industrial and commercial operations, statisticians with experience in water quality data, aquatic monitoring and modeling for groundwater and surface water, and also in evaluating sources of the environmental releases from hydraulic fracturing operations, in order to assist in reviews conducting by the SAC committee. As the DFO for this meeting, I serve as a liaison between the SAC and the agency. I am also responsible for ensuring provisions of the Federal Advisory Committee Act, FACA, are met. The Federal Advisory Committee Act of 1972 was established a system that governs the creation, operation, and termination of executive branch advisory committees. SAC meetings are subject to all FACA requirements, and these include open meetings, timely public notice of meetings, and document availability to the public. All documents are available to the public in the docket at regulations.gov, listed in the meeting agenda. As the designated federal official for this meeting, a critical responsibility is to work with appropriate agency officials to ensure that appropriate ethics regulations are satisfied. In that capacity, Committee members receive training on provisions of the federal conflict of interest laws and ethics and scientific integrity trainings. In addition, each participant has filed a standard government finance disclosure report. Our deputy ethic official for the Office of Program Support and their team, in consultation with the Office of General Counsel, have reviewed these reports to ensure all ethics requirements are met. The SAC will review challenging scientific issues over the next 4 days. We have a full agenda, so meeting times are approximate. Thus, we may not keep to exact times as noted in the agenda due to discussions and public comments. We strive to ensure adequate time for agency presentations, public comments, and committee deliberations. For presenters, SAC members, and public commenters, please identify yourself as you speak into your microphone, since this meeting is being webcasted, transcribed, and recorded. For those joining by phone, I'd like to note that we have a live video webcast of this meeting to access, so please go to the link in the meeting website listed in the agenda to join this webcast. Copies of all EPA presentation materials, written public comments, and other documents related to this meeting are available in the public docket at regulations.gov. Copies of the presentation material submitted this week by public commenters will be available in the public docket within next week. The docket number and the website are noted on the meeting agenda. For this meeting, there are so far 51 registered attendees, 9 of which are registered to give oral comments. Registration to attend this meeting is open until the last day of the meeting. Members of the committee and ad hoc reviewers are encouraged to fully consider all written and oral comments that were submitted for this meeting. We dedicated adequate time for the agency presentations, public comments, and peer reviewers to discuss their questions. As we move through the proceedings, if time allows, we may be able to move to the next agenda item if the item takes less than the anticipated time. For members of the press, EPA media relations staff are available to answer your questions about this meeting. Please address all questions to Kathy Milburn and her email or email to press@epa.gov. At the conclusion of the meeting, the SAC will prepare a report and a response to questions posed by the agency, background materials, presentations, and public comments as well. This final report also serves as the meeting minutes. We anticipate the final report and meeting minutes to be completed in 60 days after the meeting is concluded. Again, I wish to thank the committee, the ad hoc peer reviewers, and the public for their participation. I'm looking forward to both a challenging and interesting discussion over the next 4 days, and I now turn the meeting over to our chair, Dr. George Kopp. Dr. Kopp?
Thank you, Allah, and thank you to all of the staff that are supporting this committee. It's a daunting task, and I truly appreciate it. I'd like to welcome everyone to the meeting of the Science Advisory Committee for Chemicals, and thank all of our members and ad hoc members for the diligent work that you've done in reviewing this 1,4-dioxane supplement. I'd further like to commend the EPA for conducting this supplemental assessment. As noted in the documents that we're reviewing, in 2019, this committee reviewed an original assessment for 1,4-dioxane, in which air and drinking water were excluded. And the committee at that point noted that these routes of exposure should actually be included in the assessments, not only of 1,4-dioxane, but of other chemicals that were coming through the TSCA process. And to their credit, the EPA took that advice and went back and did the work that we're now reviewing today. So this is an important example of the work that we're doing and how it fits into the EPA regulatory framework and the importance of the work that you folks on the committee are doing. So I again commend the agency, and with that, I think we can get directly to the meeting. Allah, would you like me to call the roll, or are there other
Yes,
business?
please. Yes, please.
So let me do the roll call, and if I'm looking away from the screen, it's because the thing I need to look at is over a little bit to my left. So first, the full committee members, Dr. Apti.
Hello, my name is Udayan Apte. I'm a professor of toxicology at University of Kansas Medical Center, and my expertise is in effect of environmental chemicals on the liver.
Thank you. Dr. Baker.
Here, I'm Marissa Baker. I'm a faculty at the University of Washington in Seattle. My expertise is in exposure assessment and industrial hygiene.
Thank you. Dr. Chasen.
Hello, I'm Chris Chasen. My expertise has been in risk assessment methodologies and models to calculate exposure to the general population and unique communities.
Thank you. Stephanie Ike.
Good morning. My name is Stephanie Ike. I'm an assistant professor at Emory in the Department of Environmental Health, and I have a secondary appointment in the Department of Epidemiology. My research focuses on the effects of environmental chemicals on susceptible populations, particularly during pregnancy, and I'm trained as an epidemiologist.
Thank you. Dr. Fox.
Hello, Mary Fox. I'm an assistant professor of health policy and management at the Johns Hopkins Bloomberg School of Public Health. My area is environmental and occupational health policy with a specialty, I guess, in chemical mixtures and cumulative risk assessment.
Thank you. Dr. Graham.
Hello. I am an independent toxicology consultant, and my expertise is in sensitization and occupational asthma.
Thank you. Dr. Heiger-Bernays.
Hello, my name is, I'm Wendy Heiger-Bernays. I'm a professor at the Boston University School of Public Health in the Department of Environmental Health. My expertise is in toxicology and health risk assessment.
Thank you. Allison Jenkins. Is she here?
Yes, I'm here. Good morning. I'm Allison Jenkins. I'm a senior toxicologist at the Texas Commission on Environmental Quality in Austin, and I'm a regulatory toxicologist.
Thank you. Dr. Merced Neves.
Good morning. My name is Francesca Merced Nieves. I'm an assistant professor at the Department of Pediatrics and Environmental Medicine and Public Health at Icahn School of Medicine at Mount Sinai. And I'm trained as a neuroscientist, so my expertise are neurotoxicology and environmental pediatrics.
Thank you. Dr. Messerling. You here? We'll come back. Dr. Ottinger.
Good morning. I'm Marianne Ottinger. I'm an emeritus professor and research professor at the University of Houston. My expertise is in endocrinology, ecotoxicology, and I have further research background in comparative biology of aging and neurobiological disease.
Thank you. Dr. Prisbilla. She was having audio difficulty before.
Good morning. Yes, I'm on my phone. Apologies. Still working on connectivity issues. My name is Jennifer Prisbilla. I'm an environmental health scientist at the Agency for Toxic Substance and Disease Registry. My expertise is in environmental health assessments and environmental epidemiology. Thank you.
Thank you. Dr. Wright.
Hi, I'm David Reif. I'm a chief of the predictive toxicology branch at the National Institute of Environmental Health Sciences. And my expertise is in advanced analytics, computational toxicology, bioinformatics, and AI ML applications.
Thank you. Dr. Rubin?
Good morning, Rainbow Rubin, Director of Science at Breast Cancer Prevention Partners. I'm an environmental health scientist with expertise in environmental epidemiology and toxicology and exposure assessment among vulnerable subgroups.
Thank you. Dr. Rumpler?
Good morning. Mark Rumpler. I'm a clinical laboratory director with expertise in toxicology, laboratory medicine, and public health.
Thank you. Dr. Voorhees?
I think he will join later this afternoon.
Okay, thank you. Michael Wright?
Hi, my name is Mike Wright. I'm retired from the United Steelworkers Union, where I was the Director of Health, Safety, and Environment. I was trained in environmental health sciences. My expertise is in industrial hygiene, workplace exposure assessment, means of control, and the communication of chemical information.
Thank you. Dr. Bennett?
Good morning. I'm Steve Bennett with the Household and Commercial Products Association. I'm a chemist by training, and I lead our scientific and regulatory team. I have expertise in consumer and commercial use and exposure that I'll bring to the panel. I was also on the original panel for 1,4-dioxane, and like Dr. Cobb mentioned, I'm pleased to be back on and delve into some of the scientific issues we raised previously.
Thank you. Dr. Barakol?
Hi, I'm a professor in the Department of Statistics at University of California, Irvine. I am a statistician, and my expertise is in Bayesian modeling of exposure and modeling the effect of exposure, environmental exposure on health outcomes.
Thank you. Dr. Clark?
Good morning. I'm Cassie Clark. I'm a postdoctoral fellow at the Yale School of Public Health in the Cancer Prevention and Control Program. And my expertise relates to exposures and health outcomes associated with oil and gas activities.
Thank you. Dr. Ginsburg?
Good morning. I'm Gary Ginsburg. I direct the Center for Environmental Health here at New York State Department of Health, but in no way are my comments representing official policies or positions of New York State. I also have a faculty appointment in the Yale School of Public Health. I'm trained in toxicology.
Thank you. Dr. Henneman?
Good morning. I'm Lucas Henneman, Assistant Professor of Environmental Engineering at George Mason University. My expertise is in air quality modeling, exposure, and health impacts.
Thank you. Dr. Jajak?
Yeah, my name's Mike Jajak. I'm a private consultant these days, and my expertise is in near-field exposure assessment.
Thank you. Dr. McKenzie?
Good morning. I'm an associate professor at the Colorado School of Public Health at the University of Colorado. My expertise is in environmental epidemiology, exposure assessment, and risk assessments. And for this panel, those exposures and health effects around oil and gas development.
Thank you. Dr. Malinga?
Hi, my name is Andrew Maglino. I am a physical scientist at the US FDA Center for Veterinary Medicine. My expertise is in risk assessment and environmental fate modeling. My comments are my own. They do not represent US FDA.
Thank you. Dr. Portier?
Hi, I'm Ken Portier. I'm a biostatistician, applied statistician, retired, and I was previous chair of the July 2019 SAC committee that reviewed 1,4-dioxane. My expertise, as well as in statistics, is in evaluating these risk modeling, including Monte Carlo methodology.
Thank you, Ken. Dr. Potter?
Good morning. This is Tom Potter. I'm an environmental chemist
I'm currently working as an independent consultant, retired from the USDA Agricultural Research Service. My expertise is in the area of environmental fate and transport assessment and modeling.
All right, thank you. Let's go back. There's Dr. Messerlin. Is she here? Okay, and Allah, you said Dr. Voorhees will join later?
Yes. Yes.
Okay. So we have quorum, and we won't have to do introductions in the future, but thanks everyone for introducing yourself so that the public will know the folks that are on the committee and what your respective expertise are. So with that, I believe we go into the presentations by the EPA.
We're going to start with the introduction and welcome remarks by Jeff Morris, the Director of the Existing Chemicals Risk Assessment Branch of the Office of Pollution Prevention and Toxics in the Office of Chemical Safety and Pollution Prevention in EPA.
Thank you, Allah, and good morning, everyone. I want to also extend my welcome to all the SAC members, in particular the new members. Thank you all for your service, not only to our office, but to the EPA and to the American public. You know, as Dr. Cobb mentioned, this supplemental evaluation enhances the 2020 1,4-dioxane evaluation in some important ways. It extends our evaluation to the general population through air and water pathways, and also evaluates exposures to 1,4-dioxane generated as a byproduct of chemical processes such as ethoxylation and sulfonation. And the charge questions that you'll be addressing this week, looking at probabilistic approaches, aggregate exposure, the relationship between monitoring data and modeling, will enhance not only this particular supplemental evaluation, but our TSCA program going forward. And it's this dual aspect of your review this week, this support for enhancing this particular evaluation while at the same time advancing the science for the TSCA program, brings up a balancing act that I want to talk a little bit about in these few minutes that we face as regulatory scientists within EPA administering the TSCA program. Now, Rochelle Bahati is going to get into this in more detail in a few minutes, but I just want to mention we work to balance both the scientific standards embedded in TSCA to ensure that we're using the best available scientific information, applying a weight of the evidence approach, and ensuring that we are transparent and robust in doing so. That's important because the evaluation that this supplement will present will inform any action that the agency takes to address unreasonable risks that may be identified and have been identified in the draft risk of determinations gone out with this evaluation. At the same time, the TSCA space is a very large one. Tens of thousands of chemicals remain unevaluated. So it's important that we move purposefully through this space. So the timelines that are also part of the law and are equally important to the scientific standards are extremely important in making sure that we address risks in a timely way. We've been working, as you know, on 1,4-dioxane for over 6 years now. We are very much hoping that your advice this week can help us move along with public comment toward finalizing this evaluation as soon as possible. Extremely important so that we can make sure that we get any necessary protections in place. At the same time, ensuring that we make those decisions in a way that is informed by the best available science. At the same time, the advice that you will provide this week will go beyond this evaluation and help our approaches to integrating monitoring data with modeling approaches advancing our use of probabilistic assessments, and ensuring, as the statute requires, that we fulsomely consider aggregate exposures to chemical substances. So all of these considerations are extremely important. They do require a balancing. So to the extent that your advice this week can help us advance this assessment, move it purposefully and promptly toward finalization, and at the same time improves our program going forward, we thank you again and welcome a robust discussion this week.
Thank you very much for that presentation, and we do look forward to working very closely with the agency on this and other matters. So do you want to introduce your colleagues, or do you want us to do that?
Either way, you can go ahead.
Okay, so our next presenter is Dr. Rochelle Bulhati. I hope I got that name right.
Right.
And going to talk about existing chemical overview.
Hi, good morning. Welcome. My name is Rochelle Bahati. I'm a branch supervisor in the Existing Chemicals Risk Assessment Division within the US EPA's Office of Chemical Safety and Pollution Prevention. We are responsible for conducting risk evaluations for existing chemicals under the Toxic Substances Control Act. I supervise much of the work you will hear about today, including the completion of the 2023 draft supplement to the 1,4-dioxane risk evaluation. My team and I prepared a series of presentations to provide you with a summary of several new exposure assessment methods and explain how we integrated these methods into the 2023 draft supplement to the 1,4-dioxane risk evaluation. My colleagues and I want to thank you for joining us today and your willingness to offer your scientific expertise to the US EPA by serving on this panel. The feedback that you provide as part of the Science Advisory Committee on Chemicals is instrumental in how we move forward with advancing risk evaluation methods under the Toxic Substances Control Act. We look forward to receiving your feedback on the charge. To get us started, I'm going to provide you with a high-level overview. The Toxic Substances Control Act, or TSCA, of 1976 provides the US EPA with the authority to require reporting, record keeping, and testing requirements and restrictions relating to chemical substances or mixtures. TSCA was amended and updated in 2016 by the Frank R. Lautenberg Chemical Safety for the 21st Century Act. The update included standards for chemical risk determinations. Specifically, Section 6 permits assessment and reassessment and regulations of chemicals that are already permitted to be manufactured and used in the United States to ensure ongoing safety. We call these chemicals existing chemicals. For existing chemicals, the US EPA must determine that the continued use is not likely to present unreasonable risks to human health or the environment, including potentially exposed or susceptible subpopulations. The TSCA amendments mandate that the US EPA evaluate existing chemicals. This comes with clear and enforceable deadlines. In addition, the US EPA must use the best available science using reasonably available information and make decisions based on the weight of scientific evidence. Chemical assessments must be risk-based and not consider costs or other non-risk factors in its evaluation. And as I previously mentioned, risk evaluations must also consider risks to potentially exposed or susceptible subpopulations. For those identified unreasonable risks, said risks must be addressed. This means conditions of use may be modified or eliminated, or other regulating actions such as do not release may be implemented. I will speak more on the conditions of use on an upcoming slide. As mentioned, TSCA provides science standards by which the US EPA must evaluate existing chemicals. These include using the best available science that is reasonably available.
Shown on this slide is the relevant definitions provided in the 2017 risk evaluation rule that explains the procedures for completing chemical risk evaluations under amended TSCA. This is available for your reference, but in summary, the US EPA will be transparent and reasonable and use defined and systematic procedures, methods, and processes that includes use of reliable, unbiased information for the regulation of chemicals. We need to use data that are consistent with the intended use, that is the regulation of chemicals under TSCA. Therefore, the data needs to be useful for our purpose and relevant to the decision. Our risk evaluations are not research papers. They are regulatory documents with very defined purpose. We must use the information we have available at the time we are completing the risk evaluation. Any information we receive past the defined point in time can help us with future evaluations or method development. That is, we have to use the data we have at our fingertips. To this end, the US EPA develops chemical risk evaluations. The purpose of the risk evaluation is to determine whether a chemical substance does or does not present an unreasonable risk to health or the environment under the conditions of use. Conditions of use, or COUs, are the circumstances under which a chemical substance is intended, known, or reasonably foreseen to be manufactured, processed, distributed in commerce, used, or disposed of. Examples of conditions of use include manufacturing, processing for recycling, consumer use as an automotive degreaser, and disposal. The risk evaluation is the primary decision support document the US EPA uses to make risk determinations. And if we must issue regulations to address unreasonable risks identified as part of the risk evaluation, the risk evaluation informs risk management approaches to resolve the unreasonable risk. As mentioned, the risk evaluation is the primary decision support document. As such, understanding the subject chemical is important, and considering how the chemical would be managed in terms of any identified risks sets the expectations for the risk evaluation. That is, our risk evaluations need to be fit for purpose. Spending a lot of time and effort to do analyses that cannot be used in risk management or is not needed to support a decision is not an effective use of resources. I want to reiterate, our risk evaluations are not research papers. They are regulatory documents with a very defined purpose. The US EPA must complete risk evaluations within 3 to 3.5 years. This time includes not only the completion of the risk evaluation, but it also includes peer review and multiple public comment periods, along with the completion of the risk determination. This means the actual time to complete the science aspect of the risk evaluation is short. As such, the method and approaches you are being asked to review must be adequate to derive risk estimates, sufficiently robust to support an unreasonable risk determination and subsequent rulemaking, as well as be feasible to complete within the necessary time. The development of an individual risk evaluation, as well as the overall risk evaluation process, is an incremental and iterative process. We learn from each risk evaluation and modify and further develop new assessment methods and approaches to improve TSCA risk evaluations moving forward. However, as mentioned, we must use the information we have available at the time we are completing the risk evaluation. Any information we received past the defined point in time can help us with future evaluations or method development. We use several processes to get feedback on our risk evaluations, as well as the methods we use to develop them. All are consistent with the US EPA's peer review handbook and include public comment periods and peer review as required under TSCA. We have several internal peer review mechanisms, including technical teams, committees, peer-to-peer review, as well as senior staff reviews. We often collaborate across offices within the EPA, including the Office of Pesticide Programs, the Office of Research and Development, the Office of Water, and the Office of Air and Radiation. We also have several ways to seek external peer review. This SAC panel is an example. Other examples include contract or letter reviews. We may also use the journal publication process to obtain review and feedback on approaches we are developing. We also engage with stakeholders to solicit feedback. One way this is done is through workshops. For example, we have convened a series of stakeholder workshops for input on various topics, including the ongoing workshop series devoted to improving occupational exposure assessment. The first of these workshops was held in January of 2023. A second workshop is planned in this upcoming October, with additional meetings possible in the future. We also work with other government organizations like the Occupational Safety and Health Administration and the National Institute for Occupational Safety and Health. From these efforts, we can learn and implement better processes for going forward in future risk evaluations. Feedback given by this SAC panel will aid the EPA in deciding when and how to use modeling approaches to estimate potential exposure to chemicals, assist the agency in quickly identifying readily available data that's best utilized in our risk evaluations, define conditions when a specific model or evaluation strategy is applied, and aid in further method development that can be utilized in currently ongoing or future risk evaluations. Now let's transition to 1,4-dioxane. 1,4-dioxane is a liquid used primarily as a solvent in a variety of commercial and industrial applications, including reactions used to make PET plastics and in the ethoxylation reactions used to make surfactants that end up in lots of soaps, detergents, and cleaning products. 1,4-dioxane can be produced as a byproduct of chemical processes. As such, it may end up in commercial and consumer products that can result in occupational, consumer, and general population exposures. This process will be described on the next slide, but first let's discuss potential health effects resulting from 1,4-dioxane exposure. Evidence in animals shows that 1,4-dioxane increases cancer risk for a range of tumor types, including in the liver and the respiratory tract. It also has non-cancerous effects in the liver, kidneys, and in the olfactory epithelium. As a result, 1,4-dioxane is listed under several environmental statutes, including being listed on the Toxic Release Inventory since 1987 as a hazardous air pollutant, or HAP, under the Clean Air Act, and as a hazardous substance under CERCLA, and listed under the Safe Drinking Water Act's candidate contaminant list, and identified in the third unregulated contaminant monitoring rule, UCMR, or in this case, UCMR 3. Illustrated on this slide is how 1,4-dioxane produced as a byproduct results in various human exposures. As you can see, when 1,4-dioxane is produced as a byproduct of manufacturing through chemical processes such as ethoxylation, sulfonation, and esterification, it can result in direct exposures to workers on site, shown as the occupational exposure on the top of the middle of this figure. Consumer and worker exposures can also occur through use of consumer and commercial products, shown in the bottom half of this figure. General population exposures from releases to air and water, shown on the right side of this figure, may occur. As you can see, 1,4-dioxane produced as a byproduct is relevant to several conditions of use and exposure pathways. 1,4-dioxane has a history of evaluation, as you've heard, within existing chemicals risk assessment division. In 2020, a risk evaluation was completed, considering acute, chronic, and cancer effects that I previously described. The 2020 risk evaluation evaluated several exposure pathways, including occupational, consumer, and general population. As a result of this work, the only unreasonable risk identified for 1,4-dioxane was occupational exposures, where 13 of 16 conditions of use were determined to have unreasonable risk. No unreasonable ecological risk was identified. I have links to the science documents on this slide for your easy reference. In January of 2021, the White House issued Executive Order 13990, instructing agencies to follow the science, improve public health, and protect the environment, limit exposure to dangerous chemicals, and prioritize environmental justice. It also instructed agencies to review actions taken during the prior administration to consider suspending, revising, or rescinding such actions. In the case of 1,4-dioxane, we determined that the 2020 risk evaluation excluded known human exposure pathways that are important to understanding the health implications of 1,4-dioxane. The decision was made that a more complete evaluation was needed, and a supplement to the 1,4-dioxane risk evaluation would allow the agency to comprehensively address potential risks. As part of this more complete examination, it was highlighted that the water pathway needed additional examination because multiple types of sources contribute to 1,4-dioxane concentrations in water. 1,4-dioxane is persistent in water, and 1,4-dioxane has also been detected in finished drinking water in some locations. In addition, 1,4-dioxane is produced as a byproduct. Its production as a byproduct is an interesting challenge because it is common and it contributes to human exposures. However, some industries that are producing 1,4-dioxane unintentionally as a byproduct may not even be aware of its presence. This supplement to the 1,4-dioxane risk evaluation aims to address the critical gaps that the 2020 risk evaluation, specifically by evaluating occupational exposures to 1,4-dioxane produced as a byproduct and by evaluating general population exposure pathways, including drinking water and air, excluded due to a policy decision. The 2023 supplement does not revisit analyses completed in the 2020 risk evaluation. So we continue to rely on our 2020 findings related to the physical chemical properties, environmental fate and transport, hazard identification, and dose response information. Furthermore, the 2023 supplement does not revisit previously assessed occupational and consumer exposures. The current supplement is focused on evaluating the exposure pathways not previously evaluated. The 2023 supplement was developed in coordination with other EPA offices. We developed several new analysis methodologies and approaches that have not been applied to TSCA risk evaluations, as you will see in the forthcoming slides. We apply these methods in the context of 1,4-dioxane and present them to you as a case study and how these methods and approaches can be applied to a TSCA risk evaluation. I emphasize that the charge for this panel is on the proposed methods and evaluation strategies overall and not the results as shown for 1,4-dioxane. As mentioned, my team has prepared a series of presentations to provide you with a summary of several new exposure assessment methods, which I have outlined on this slide. You will see this figure throughout our presentations to help orient you throughout the day. You will see references to the topic, the charge question, as well as the location of the necessary documentation. We are seeking review of the Monte Carlo modeling used in this assessment of occupational exposures and environmental releases, as well as consideration of hydraulic fracturing as a condition of use. These topics will be presented to you next by Franklin Hall. We are seeking review of the drinking water exposure assessment methods used to assess general population exposures to 1,4-dioxane present in surface water and groundwater that is sourced for drinking water. You will hear about the surface water exposure assessment from Jason Todd and Brian Groza. In these presentations, they will describe advancements made with respect to streamflow data and the use of community drinking water intake location data. Sean Shiflett will provide you with an overview of a groundwater exposure assessment. In his presentation, you will learn about a novel model application and TSCA risk evaluations. We are seeking feedback on the methods used to consider aggregate exposure for 1,4-dioxane, and our approach will be presented to you by Kevin Villamere. To conclude our presentation, Susanna will provide you with a wrap-up. Before we turn over to the technical presentations, I wanted to turn the microphone over for Franklin. I can take any clarifying questions that you may have. Thank you again for being here today. We look forward to your feedback on the charge.
Thank you. So you had asked for questions. I think Allah had saved the questions till later, but I think we can take some questions now, Allah, if you don't object. So are there clarifying questions from the committee? And I can't see if there's anyone's hand is raised. Oh, there's Dr. Barakal.
Yes, this is Dr. Barakal. I have a question, but it's not really related to the charge question. It's more for me to understand, because in the document and also in this presentation, you have mentioned several times unreasonable risk, and I was wondering whether there is a specific definition that is used to determine a reasonable risk.
You can, or you can turn yours if you're on.
Huh? Hey everyone, this is Jeff Morris. Thanks a lot for the question. There isn't in the law or in our regulations any particular definition of unreasonable risk. As a starting point, we look at the typical benchmarks that the EPA uses for cancer and non-cancer risk, as well as risk to the environment. For example, for cancer risk, you might look at a benchmark between 1 in 10,000, 1 in a million additional cancer cases for unreasonable risk. But that's just a starting point. We also look at the nature of the effect, the uncertainties around the risk estimate, population exposed, a number of factors. So it's really sort of a holistic approach to looking at the factors around that risk estimate that drive whether or not the agency determines that the risk is unreasonable. So I hope that's helpful. And perhaps as we go through the evaluation, it may sort of elicit other questions around that. But that's our approach. And again, if that wasn't clear, let me know. But you know, just yeah.
Okay. Thank
Is that
you.
helpful? Sure.
Thank you. Dr. Jajak?
Yes, thank you. Yeah, these are incredibly basic questions vis-a-vis significant risk. My question is the agency's, what's the agency's thinking now relative to occupational versus non-occupational risk? Historically, they've been much different, but I'd like to hear what the thinking is today.
Let me ask, if you mean for cancer risk, for example, how the agency has typically looked at a standard for occupational risk of around 10 to the minus 4 or 1 in 10,000, and general population sort of a range between 10 to the minus 4, 10 to the minus 6. It made that differentiation between occupational and general population consumer risk with respect to where we might look at benchmarks. Is that the question? Because that's still, in a general sense, the way we approach it.
Yeah, so what I'm hearing is there's still this differentiation between occupational, non-occupational acceptable risk for carcinogens.
There can be, of course, but again, you know, we look at the benchmarks as just that, as benchmarks, a starting point. We don't look at them as bright lines. So, you know, we do recognize that there's always a range. And of course, it depends on the nature of the worker population too. How big is that population, et cetera. So, but still, when we do, and you'll see in our evaluations and in our risk characterization, there is something of a distinction, yes.
Okay, thank you.
Just reminding everyone, because this is transcribed, that you state your name before you speak, please. Thank you.
Thank you for that reminder, Ala. This is George Cobb. And thank you to the EPA presenters. One thing I'd like to mention is we're going to welcome all questions. If you have generic questions, let's save them for the question and answer period after the presentations. And try to, if you have clarifying questions right after some of these presentations, we may have time for them. We actually may not as well. So now I believe the next presenter from EPA is Franklin Hall to talk to us about occupational exposures. Do we have audio?
Okay, good morning. Can everyone see me? Okay.
Yes.
Excellent. Excellent. Good morning, everyone. My name is Franklin Hall, and I am the chemical engineer for the 1,4-dioxane assessment, and we'll be covering the occupational exposure and the environmental release assessment. The engineering presentation is broken into two parts. The first part will provide an overview of the engineering assessment with the intention of familiarizing you with the components of some key approaches. The second part of the presentation will provide an overview of the Monte Carlo applications in the assessment with a focus on components which are the source for the charge questions to the panel. This information is described in section 2.1 and 2.2 of the risk evaluation, with additional detail provided in appendices D and E. I would like to point out that the sections I'm presenting today provide context and information relevant to charge question 1, which solicits comments on the application of Monte Carlo method components in the assessment of exposures and releases from several occupational exposure scenarios. Although this supplement to the risk evaluation for 1,4-dioxane is a specific application of these methods, it's important to remember that the charge questions are soliciting comment on the methodology, using the presentation of the 1,4-dioxane application as an example. Before getting into the overview, I want to highlight the terms condition of use, or COU, and occupational exposure scenario, or OES. These terms are used throughout the assessment and warrant some brief explanation. The key term in this pairing is OES. OES are used to organize COUs for environmental release and occupational exposure assessments. This organization involves mapping and grouping based on similarities and differences between COUs, as well as data availability. It is important to note that COUs are not created during this mapping process, and that all OES map to at least one COU. COUs may be organized into OES in many ways, as shown in the diagrams on this slide and described in the text and examples below them. The supplemental risk evaluation includes water, air, and land release estimates for all OES, including both those in the original risk evaluation and the byproduct related OES added in the supplemental risk evaluation. The original risk evaluation did include water estimates, but these are replaced by those in this supplemental risk evaluation because the supplemental risk evaluation includes more comprehensive estimation approaches. For each occupational exposure scenario, a daily water release was estimated based on annual releases, release days, and the number of facilities as shown in this diagram. The blue boxes show the primary sources of data to develop annual releases, release days, and number of facilities. In general, EPA used TRI and DMR data to estimate releases. However, where releases are expected, but TRI and DMR data were not available, releases were estimated using data from other sources, such as emission scenario documents, generic scenarios, and process description information. In general, we prefer measured data or data that has been estimated using documented approaches, such as that from TRI and DMR. Where these data were unavailable for an OES, EPA modeled releases. These modeling approaches include models from generic scenarios and emission scenario documents. Some of these models include Monte Carlo simulation, depending on data availability. Additionally, EPA used assumptions based on process description information. For example, if process description information indicates there are no releases or that a certain % of the use rate is released, EPA may use that information to inform the release estimates. For reference, section 2.2.1.1 of the risk evaluation contains maps such as the one shown here, which presents reported 1,4-dioxane annual releases, reported release data for, indicating the range of release along with the source of the release. This map only shows reported release data from the TRI and DMR and not from modeled release estimates. In considering release estimates for all OES, the largest water releases were from the PET manufacturing OES, which was based on TRI data. The largest land releases were from the disposal OES, which was based on TRI data, and the largest air releases were from the hydraulic fracturing OES, which was modeled. The release estimates in this assessment are based on the best reasonably available data and assessment approaches. However, it should be noted that as with any estimate or even measured value, there are assumptions, uncertainties, and limitations. Some of the key considerations are shown in this slide. For example, reported information presented in programmatic databases are sometimes limited, which can introduce uncertainty in mapping the reporting sites to the applicable conditions of use and subsequently the corresponding occupational exposure scenarios. For modeled releases, uncertainties and limitations are predominantly associated with the data availability, which impacts the ability to define model input parameters. Weight of scientific evidence conclusions are based on a variety of factors, including some of the uncertainties and limitations in this slide. Next, we will discuss the occupational exposure assessment, which is described in section 3.1 of the draft supplemental risk evaluation with more detail in Appendix F. Please note that the supplemental risk evaluation only includes occupational inhalation and dermal exposure estimates for those occupational exposure scenarios that were not assessed in the 2020 risk evaluation, which are the byproduct-related occupational exposure scenarios listed in this table, in this slide. Occupational exposure scenarios with estimates in the 2020 risk evaluation were not reassessed in this supplemental risk evaluation. The components of an occupational exposure assessment are listed in this slide. The first step is to understand the OES by developing a process description that includes information on worker activities and potential points and routes of exposure to 1,4-dioxane. For each OES, we estimate the number of sites, number of workers, and number of occupational non-users based on information from programmatic databases, literature, and exposure and release profile documents such as generic scenarios and emission scenario documents. Finally, we estimate inhalation and dermal exposure estimates for each OES using either monitoring data or modeling, which we will discuss in the upcoming slides. For reference, the term occupational non-users refers to workers whose activities do not require them to handle 1,4-dioxane. However, they may be indirectly exposed due to the proximity of their workspace to an area where 1,4-dioxane is present. To assess inhalation exposure for workers and occupational non-users, EPA used both monitoring data and modeling approaches. Where monitoring data are available, EPA used personal breathing zone data for 8-hour exposures from directly applicable scenarios or similar scenarios if directly applicable data were not available. Where monitoring data were not available, EPA modeled inhalation exposures using Monte Carlo methods and models in generic scenarios, emission scenario documents, or existing OPPT models. These exposure estimates were then used to calculate average daily concentration and the lifetime average daily concentration. To assess dermal exposure, EPA used the dermal exposure to volatile liquids model to calculate the dermal absorbed dose. The equation modifies the EPA two-hand dermal exposure liquids model by incorporating a fraction absorbed parameter to account for the evaporation of volatile chemicals. This parameter is a function of air speed within indoor environments, which differs for industrial and commercial settings. This approach is unchanged from that which was used in the 2020 risk evaluation. As with the environmental release estimates, the occupational exposure estimates are based on the best reasonably available data and assessment approaches. Similarly, it should be noted that there are assumptions, uncertainties, and limitations associated with the exposure estimates. Some of the key considerations are shown in this slide. For example, inhalation monitoring data were often limited to small data sets from older monitoring events. With respect to modeled inhalation exposures, uncertainties and limitations are mostly impacted by data availability, which subsequently affects the ability to define model input parameters. For dermal exposures, the model used was limited by the fact that it does not incorporate variability in the exposure, duration, and frequency. However, the assessment approaches represent reasonably available data and the best available science. In this part of the presentation, we will discuss the use of Monte Carlo methods for modeling environmental releases and occupational exposures. The general modeling approach is described in Appendix E10 of the risk evaluation. The two main approaches to modeling are deterministic and stochastic processes. Deterministic modeling is limited to a single output, while stochastic modeling provides a distribution of output values. Monte Carlo methods fall under stochastic modeling because they are distributions of input values to generate a distribution of output values. The expansion of Monte Carlo modeling as a methodological change in the application of existing and newly developed generic scenarios and mission scenario documents is a significant step forward in our engineering assessment approaches. Under previous risk evaluation engineering assessments, Monte Carlo application was largely limited to occupational exposure scenario models that were developed in parallel with the applicable generic scenario or mission scenario document. However, for 1,4-dioxane, occupational exposure scenarios such as laundry detergent and textile dyeing, the Monte Carlo application represents a general framework which may be used to incorporate Monte Carlo into generic scenarios or emission scenario documents that were previously limited to deterministic modeling, thereby providing a template which can be used to incorporate more probabilistic components into additional engineering assessments and future risk evaluations. The implementation of Monte Carlo methods generally follows these steps, including defining input parameters, randomly sampling the input values, executing the model calculations using those randomly sampled input values, saving the output results, repeating the previous steps for a large number of iterations, and then aggregating all the output results to calculate statistics at the central tendency, such as the central tendency and the high-end output values. Now let's talk about the process to actually build models using Monte Carlo methods. We start by building the deterministic model, meaning we define all the input parameters and calculations needed to generate the desired output, which is the environmental release or occupational exposure estimate. Then we develop the input parameter distributions based on the readily available data. Next, we select the model outputs that we want to aggregate to generate our central tendency and high-end estimates. Finally, we select the simulation settings, run the model, and aggregate the results. We will talk about each step in the coming slides, along with some examples from the 1,4-dioxane supplemental risk evaluation. The first step in building a model with Monte Carlo methods is to build the framework of the model as a deterministic model. This simply means defining the input parameters and setting up the equations in the Excel file. We're not defining the parameters at this point, but just setting them up in a tabular format. For this step, we use emission scenario documents and generic scenarios as a basis for our deterministic models. These emission scenario documents and generic scenarios typically define all the input parameters and provide all the equations that we need to estimate the environmental releases and occupational exposures. Here's an example of the implementation of step 1, building the deterministic model using the 1,4-dioxane laundry detergent occupational exposure scenario. For this OES, EPA used the 2011 emission scenario document on the chemicals used in water-based washing operations at industrial and institutional laundries, which is a peer-reviewed and published emission scenario document by the OECD. The emission scenario document defines all exposure and release points as shown on this diagram. For all release and exposure points, EPA used at least one input parameter with a Monte Carlo distribution, which is incorporated into the corresponding release or exposure output. These points are indicated by the blue text in the diagram. The variability that is introduced by the incorporation of these distributions improves the representativeness of the model outputs. Similarly, the Monte Carlo distributions were generated for the 1,4-dioxane application of the textile dyeing model. However, for this OES, EPA did not model exposures due to the existence of monitoring data. Only environmental releases were modeled using Monte Carlo components. Additionally, dust releases, shown as release point 1, were not expected. Therefore, those release and exposure points remain in black text on the diagram. When selecting which input parameters will have probability distributions, we first consider the availability of data to inform a distribution. If there is a possible range of values for a given parameter or multiple sources that provide different values for a parameter, then a distribution can be defined for the parameter. However, if there is only a single value for a parameter, a distribution does not exist. If a parameter has sufficient data for a distribution, the type of probability distribution must be determined. For this, we consider important information about the parameter, such as if it is discrete or continuous, bounded by specific values, and if there is a value that is most commonly occurring. Using that information, we can define the type of probability distribution. Some of the most common types of distributions are shown here. Here are some input parameters distributions from the model used to estimate 1,4-dioxane releases and occupational exposures during the use of laundry detergents. As you can see, some inputs are based on data from the emission scenario document, some on literature, and some on standard models. The type of distribution for each parameter varies based on the data availability. Another aspect to consider when defining input parameter distributions is the sensitivity of the model results to an input parameter. EPA may choose to prioritize the development of probability distributions for the parameters to which the model outputs are the most sensitive. Variability in these parameters may improve the representativeness of the model outputs. EPA performs sensitivity analysis on the model using the Monte Carlo plugin software at risk. The software includes built-in sensitivity analysis functions. EPA specifically conducted the sensitivity analysis using the function to calculate sensitivity based on change in output statistics, specifically the mean. Once the model simulations are complete, a user can generate an output report that includes a tornado chart for each output. The tornado chart is a bar chart with a bar for each input that is size corresponding to the impact of the input on the output mean. We'll review an example on the next slide. This slide presents an example sensitivity analysis completed for the laundry detergent model, specifically for release point 1, which is releases of 1,4-dioxane from laundry detergent container cleaning or disposal. In the tornado chart, the inputs with the largest bars are the parameters to which the outputs are most sensitive. The corresponding table lists these inputs in the order of most to least sensitive. In this particular case, the daily release quantity is most sensitive to the daily use rate of laundry detergents and the mass fraction of 1,4-dioxane in the laundry detergents. EPA uses this sensitivity analysis to ensure that the inputs with the largest impact have probability distributions to incorporate variability into the model. All the inputs listed in this example have probability distributions. For comparison, here is the sensitivity analysis for the textile dyeing model, specifically for release point 2, which is releases of 1,4-dioxane from dye container cleaning or disposal. In this case, the daily release quantity is most sensitive to the textile production rate and the container residual fractions. Prior to running the model, a few final steps need to be completed. First, we need to select the outputs for which we want statistical results. In our case, we want statistics for all releases and exposures so we can determine the central tendency and high end. The model aggregates the results from each iteration and calculates the desired statistics. Next, we need to define the number of iterations for the model simulation and the type of sampling the model uses to randomly select the input values for each iteration. For the number of iterations, we want to reduce the margin of error around the mean for each output. Essentially, we want the mean to stabilize around a single value. However, the higher the number of iterations, the longer the simulation takes to run and the lower the gains for each simulation. EPA typically finds that 100,000 iterations is sufficient to reduce the margin of error and simulation runtime. However, more iterations may be needed if the mean of the output has not converged. Although not shown here, step 5 consists of aggregating the outputs from each iteration and generating statistics such as the 50th percentile and 95th percentile for presentation and the final exposure or release estimates. EPA used this Monte Carlo approach for 4 of the byproduct-related OES in the supplemental risk evaluation: the use of textile dyes, laundry detergent, hydraulic fracturing, and antifreeze. As shown here, the emission scenario documents or generic scenarios that EPA used to model each OES. As mentioned previously, the underlying distributions are sourced from literature and the emission scenario documents or generic scenarios. As such, data availability has a significant impact on the opportunities for the incorporation of Monte Carlo in engineering assessments, not only with respect to developing distributions for key parameters, but also the ability to develop appropriately descriptive deterministic models. The use of modeling with Monte Carlo methods has some key strengths over deterministic modeling. These include the introduction of variability from the use of distributions of input parameters and the reduction of uncertainty associated with a single release or exposure estimate, as the model produces a range of estimates, which improves our confidence in the representativeness of these estimates. Another key strength is this modeling approach can be used where there is limited data available, as generic scenarios and emission scenarios can be used to fill in data gaps. However, when there is limited data, the use of these generic input parameter values adds uncertainty to the assessment because these values are not specific to sites that use 1,4-dioxane. Some of these considerations contribute to the summary of the weight of scientific evidence conclusions. Let's take, for example, the occupational exposure assessment. For dermal exposures, all OES were assessed with the same modeling approach. Therefore, they all have the same weight of scientific evidence conclusion of moderate. For inhalation exposures, the OES that are based on a limited amount of monitoring data that was somewhat older have slight to moderate weight of scientific evidence conclusions. Otherwise, the OES generally have moderate or even moderate to robust conclusions. On the right side of the slide are 2 examples of rationale for the weight of scientific evidence conclusions for textile dye and hydraulic fracturing inhalation exposures. Weight of scientific evidence conclusions is increased by factors such as the relevance of the data to the OES, the inclusion of multiple sites in the data set, and having input parameter distributions for modeling. Weight of scientific evidence conclusion is decreased by factors such as older or limited amount of monitoring data and the use of generic data for model input parameters. In the case of 1,4-dioxane, we use Monte Carlo modeling to support occupational exposure assessments for some of the COUs, hydraulic fracturing, laundry detergent, antifreeze, and textile dyes, while occupational exposure scenarios for other COUs were evaluated based on available monitoring data and other previously established methods. This slide summarizes our overall findings for occupational cancer risks from the estimated exposures for all of the newly evaluated COUs. For the new occupational COUs evaluated in the supplement, all of which are associated with the exposure to 1,4-dioxane produced as a byproduct, we estimated both central tendency and high-end exposures for inhalation and dermal routes. The take-home here is that risk estimates spread across quite a range that reflects the diversity of the COUs covered here, everything from industrial and manufacturing settings to commercial cleaners and dish soaps. Cancer risks at the high end are as high as 2 in 100 for PET manufacturing. Other COUs with the highest risk include ethoxylation processes, hydraulic fracturing, and some of the commercial product uses. I'm focusing on cancer risk here because it's the driver, but we did see acute and chronic non-cancer risks for some occupational COUs as well. The confidence in these risk estimates varies across COUs because the available data for some of these is either older or may not be representative of the whole industry. There is some uncertainty around how well the risk estimates represent current risks and how variable the risks are under different facilities within a COU. For example, for PET manufacturing, there are high risk estimates, but there is some uncertainty because older monitoring data were used, which may not reflect current exposures. For some COUs, we've been reaching out to industry to specifically invite comments on the extent to which our assessment reflects current practices so that we may improve our understanding of the variability across facilities. In conclusion, modeling with Monte Carlo methods is a powerful tool to estimate occupational exposures and environmental releases. Monte Carlo methods have the benefit of incorporating variability compared to deterministic modeling methods, as well as being useful in situations where limited data are available. However, in such situations, it's important to recognize that the use of generic data and assumptions adds uncertainty to the assessment because the data is not chemical specific. In light of the advantages of Monte Carlo methods, EPA will continue to use this modeling approach in future risk evaluations and is soliciting comment on the components of this approach. This concludes my portion of the presentation. I do have one final note that I'd like to mention, and that is that we'd like to notify you of a correction for some of the citation links within the draft risk evaluation. If you are a member of the general public and cannot access an emission scenario document, all of which should be publicly accessible, please simply replace the HeroNet part of the URL with Hero. That change should allow for full access to the document PDF. For example, the automotive detailing products and hydraulic fracturing emission scenario documents are two files that will need the URL modification in order to gain access. If you still have access issues after making this change, please let us know. Thank you.
All right, thank you very much for that comprehensive presentation. We're kind of up against a break, so I think instead of going to questions now, we will try to have a break now, and we are pretty much on schedule. So I'm grateful to EPA for keeping us on time. But at this point, I'd like to take a break and for the next maybe 12 minutes. Is that all right, Olaf?
Yes, sure.
So we will reconvene at 1/2 the hour, whatever hour you are, time zone you're in. Welcome back. So we'll proceed with our presentations. This one from Dr. Jason Todd, who's going to talk to us about surface water exposures. And whenever you're ready, take it away.
Good morning, everyone. Hello, my name is Jason Todd, and I'm a science advisor within the Office of Chemical Safety and Pollution Prevention. Today, I will be introducing the surface water exposure assessment. In particular, I will be describing and giving an overview on general population exposures resulting from environmental releases. In the forthcoming slides, we will be describing a number of novel methodologies and evaluation approaches and their application to the 1,4-dioxane supplemental risk evaluation. To place this section into context with the rest of today's presentations and orient the SAC to this review as a whole, this and the following presentation are related to questions outlined under Charge 2 and the water pathway analysis, as highlighted in orange on this slide. Within the supplemental risk evaluation, these topics are addressed in Section 2.3.1 and Appendix G. The 1,4-dioxane supplemental risk evaluation represents a product that aims to respond to both public comments and SAC peer review comments received during the initial 1,4-dioxane risk evaluation review, as well as comments received during the peer review of the draft TSCA screening level approach for assessing ambient air and water exposures to fence line communities version 1.0, or fence line assessment. During these two peer reviews, several suggestions were given on ways to bolster our methodologies and analyses for both 1,4-dioxane as well as general approaches towards evaluating surface water exposures to the general population. Shown on this slide are a few of the relevant comments received during these peer reviews. Among the topics that received multiple comments were recommendations that EPA, 1, evaluate the exposure to the general population, including the evaluation of down the drain releases and drinking water pathway. 2, consider evaluation of pests and aggregate exposure. And 3, consider available monitoring and release information, including the use of multiple years of data where possible. Let's focus for a minute on better explaining the relevance of the surface water pathway and its role in drinking water. Surface water plays an integral role in providing drinking water supply to the nation's population. As of 2015, around 282 million people, or 87% of the total US population, received their drinking water from publicly supplied drinking water. 61% of that water supply is sourced from surface water, while 39% is from groundwater. Depending on location, surface water body types, including rivers, streams, and impoundments or reservoirs across the country. Therefore, chemicals released to surface water can lead to potential exposures of the general population and can impact large portions of the country. This peer review focuses on part on the methodologies employed when evaluating surface water exposures to the general population, but physical, chemical, and release properties specific to 1,4-dioxane impact some of the employed strategies and approaches shown in forthcoming slides. Meanwhile, some of these chemical-specific properties also make 1,4-dioxane an ideal test candidate in applying some of these methodologies within surface water. 1,4-dioxane in water is of particular concern due to its multiple contributing sources within this medium, which include numerous industrial releases, as well as commercial and consumer down-the-drain releases. 1,4-dioxane is hydrophilic and readily miscible in water, and once present in water pathways, it tends to be persistent and not readily subject to degradation. Additionally, conventional drinking water treatment systems do not readily remove 1,4-dioxane during the treatment process, which results in measurable and in some cases elevated concentrations in not only ambient surface water and raw drinking water, but finished drinking water as well. Now that we've discussed the properties of 1,4-dioxane, we will now focus on the goals of the surface water assessment within the supplemental risk evaluation. Overall, our goal is to use 1,4-dioxane as a special application of improved methodologies when evaluating surface water exposures to the general population. While continuing to be a work in progress, we feel that these new approaches represent incremental forward progress when evaluating this pathway. While the approaches described in forthcoming slides may not be exactly replicable across all potential chemicals or situations, many of these approaches are adaptable for chemical-specific considerations. We welcome your comment on these approaches and strategies moving forward. To that end, we evaluate the drinking water pathway that was not previously considered in the initial risk evaluation or to this degree in previous TSCA risk evaluations. Due to its physical chemical properties, known exposure pathways, and available information, 1,4-dioxane acts as a good target chemical to evaluate these new applications and methodologies. EPA aims to improve analytical rigor with new input data sets and modeling strategies that better estimate quantitatively and qualitatively exposures to the general population through the surface water pathway. Finally, as discussed in more detail on a previous slide, we aim to be responsive to previous risk evaluation SAC and public comments. This supplemental risk evaluation aims to be responsive to both the previous 1,4-dioxane risk evaluation published in 2020, as well as the fence line assessment published in 2022. Here we highlight a conceptual model for the surface water pathway from sources to receptors that describes how chemical releases can lead to general population exposures. Sources for this evaluation include industrial facility and wastewater treatment plant releases, as well as incorporation of down the drain disposals from consumer and commercial uses. This represents the first time down the drain releases have been considered for a TSCA chemical. Our pathways of interest include ambient surface water as well as finished drinking water. Possible routes of exposure from these pathways include incidental dermal contact and ingestion through activities like swimming or recreation and ingestion of drinking water. While a possible route of exposure, the incidental dermal and ingestion routes were evaluated during the initial 1,4-dioxane risk evaluation and are not revisited in this supplemental risk evaluation. Hereafter, we focus our evaluation on ingestion via drinking water, with our receptors of interest being the general population, including possible fence line communities. To cover the range of the general population exposures, the risk evaluation considers multiple age groups ranging from infants to adults. To that end, in an effort to further evaluate the surface water pathway and effects of those potential exposures on the general population, we have implemented several revisions and/or additions to the supplemental risk evaluation of 1,4-dioxane. Several of these approaches began within the fence line assessment, but have been expanded upon here. These approaches and their application to 1,4-dioxane will be introduced here and explained more fully in forthcoming slides. In this risk evaluation, we have utilized a modified hydrologic flow database as compared to the previous 1,4-dioxane risk evaluation and other first 10 chemical risk evaluations. This flow database incorporates updated flow estimates as well as a finer resolution stream network. This improved geospatial layer and accompanying flow database aids in better linking chemical releases to their receiving water body in geographic space and hydrologic condition. These edits also provide additional analytical rigor given the importance flow has on estimating in-stream concentrations. Further, the use of this new flow database, accompanied by other EPA databases detailing drinking water intake locations, allows for possible estimation of downstream concentrations and proximity of releases to those intake locations. This is being described and shown in a TSCA risk evaluation for the first time. We have also evaluated the contribution of down the drain releases of 1,4-dioxane resulting from the use of consumer and commercial products to surface waters that was developed using a new modeling tool named eWizard. To estimate exposures across the COU, a probabilistic approach was developed that provides a distribution of expected chemical concentrations across the COU rather than at a specific facility location. Use of this model allows for better characterization of possible exposure concentrations across a condition of use, as well as informs the relative contribution of down the drain releases. Included in all these modeling approaches is the use of multiple years of input data where possible, which allows for better consideration of variability in releases year over year and the subsequent effect on in-stream concentrations. We have also evaluated the monitoring occurring at public water systems, or PWSs, of both raw or untreated source water and finished or treated drinking water. This information for 1,4-dioxane comes from a variety of sources, including the Water Quality Portal for ambient surface water, as well as data from the Unregulated Contaminant Monitoring Rule, or UCMR, and additional state databases for drinking water monitoring information. This monitoring information allows for evaluation of 1,4-dioxane found in drinking water systems directly, and also as a validity check on our modeled exposures through location-specific case studies when monitoring and release data are coincident in time, frequency, or geographic space. On this slide, I introduce a conceptual overview map describing the overall surface water approach used in this risk evaluation to evaluate exposures to the general population. It will be used to guide our various approaches in subsequent slides. At the top is the use of monitoring data. This monitoring data is used to inform known concentrations in ambient surface water and drinking water, as well as inform our facility-specific modeling and probabilistic and aggregate modeling. On the left side of this diagram is facility-specific modeling that results in point-of-release concentrations within ambient surface water and estimated concentrations as the chemical travels downstream. As shown on the right side of this diagram, the facility-specific modeling is also incorporated into a probabilistic and aggregate modeling approach that results in estimation of facility contributions. Also included in the probabilistic and aggregate modeling is estimation of down-the-drain releases and resultant in-stream concentrations, and estimation of hydrologic fracturing releases. To better explain these approaches and their application within the 1,4-dioxane supplemental risk evaluation, I will now hand it over to my colleague, Brian Groza. Thank you.
Thanks. Good morning. I'm Brian Groza, a physical scientist in the Office of Chemical Safety and Pollution Prevention. And this section of the meeting, it will focus on updates to the surface water sourced drinking water pathway, which have been applied in the supplement to the 1,4-dioxane risk evaluation. For each new aspect of the surface water approach being presented, the general approach will be discussed, as well as the 1,4-dioxane specific application included in the draft supplement. The first few slides will describe updated inputs to the basic underlying facility-specific modeling methodology, which is based on the EFAST 2014 approach for releases to surface water. This methodology serves as the starting point for the more advanced modeling applications employed in the supplement. Concentrations in receiving water body at the point of release are primarily calculated from the facility release data and the receiving water body hydrology. Updates to these inputs include a more modern hydrologic flow database, a hierarchical approach to associating releases with water bodies, and assumed release amounts for facilities without explicitly reported values. This information is relevant to charge questions 2.1 A and B, which refer to the updated hydrologic flow data and assumptions made in cases where releases or water body data were not available. EPA included hydrologic data from the National Hydrography Dataset, called NHD Plus version 2.1, as an update to the hydrologic data previously used in surface water assessments for TSCA risk evaluations. This database is a joint EPA-USGS product that includes over 1.7 million flow lines across the conterminous United States. And there's a small snapshot of that shown in a map just to give you a sense of the scale. For each flow line, the database includes mean annual and monthly average modeled flows, which have been developed from a runoff model and calibrated to USGS stream gauge observations. The flow line network includes downstream connectivity information, which can be applied to search downstream from a point of release. It has also been incorporated into other agency databases, such as being referenced by the National Pollutant Discharge Elimination System, or NPDES permits, to identify the specific water body and reach receiving effluent from a facility. The flow database originally embedded in the EFAST 2014 model and previously applied for the TSCA risk evaluations is a predecessor of the NHD database and is called REACH File 1. The NHD Plus was developed to represent streams visible at a 1 to 100,000 scale, as opposed to the 1 to 250,000 mapped scale of REACH File 1. As shown in the example maps of New Hampshire here on the left, the NHD Plus database provides more complete coverage of the stream flow network across the country, allowing more accurate assignments of receiving water bodies and less dependence on surrogate flow data. This figure shows a red dot representing a hypothetical point of release to demonstrate how the updated flow database contains flow lines more likely to represent the immediate receiving water body rather than a reach further downstream, and also better matching to the actual receiving watershed. Due to the inclusion of finer resolution flow lines, the overall distribution of flows, which is shown in the histograms on the right, shift towards lower values in the updated data set. The resulting in-stream concentrations from releases are highly sensitive to the flow in the receiving water body. So model discharges to smaller streams is expected to result in greater concentrations at the point of release. EPA therefore believes that this more refined data set not only produces more conservative, but more accurate modeled point of release concentrations. EPA applied a hierarchical approach to assigning REACH codes of receiving water bodies to discharging facilities. Whenever possible, the REACH code listed as the receiving water body under an NPDES permit for a facility would be used. If a REACH code was not available from a permit, a geospatial analysis was conducted to locate the nearest NHD Plus REACH. A 2-kilometer limit was applied to this search so as not to erroneously match facilities to flow lines too far away from the facility. If no REACH was found within 2 kilometers, the lowest non-zero flow from a facility within the same OES grouping was substituted for the facility with the missing flow data. From the NHD Plus dataset, the QE modeled flow values were used, which are recommended in the NHD Plus documentation as the most representative of the actual average stream flow values. In some cases, these modeled values were used to calculate additional flow statistics, such as the harmonic mean, using regression equations applied in the EFAST model. While these regression equations were originally developed with a 30Q5, or lowest 30-day average flow in a 5-year period, the lowest of the modeled monthly average flows was substituted for this value in the regression calculations. Now let's take a look at how often certain assumptions had to be made about release and receiving water bodies within the supplement. This table presents a breakdown of how the 1,4-dioxane facilities releasing to surface water, both the direct and indirect releases, were associated with receiving water bodies. Over 70% of facilities included a receiving REACH code in their NPDES permit, while another 15% were able to be assigned to a REACH within 2 kilometers, and the remainder used some substituted data from other facilities. Facilities discharging up to 500 pounds of a chemical per year may report to TRI via a Form A. In the interest of including all facilities reporting surface water discharges to TRI, facilities reporting with Form A were included in the release analysis, and the conservative assumption was made that those facilities were discharging 500 pounds per year. And there's an accounting of the percent of each facility within an OES that were reporting with Form A on the right. A sensitivity test of the degree to which some lower confidence input data were affecting results and conclusions drawn from this surface water analysis was conducted by removing facilities where some assumption had to be made by exposure assessors with respect to the amount of release and the receiving water body associated with the facility. This left only facilities for which a REACH code of a receiving water body was able to be retrieved from an NPDES permit, and those facilities reporting release amounts via TRI Form R or DMR with actual or estimated amounts. Overall, while there was some shift of the median and 95th percentiles towards slightly lower values, the distribution was not impacted too dramatically by the exclusion of these facilities. The minimum and maximum values remained unchanged, and the general shape of the distribution was preserved. In the case of 1,4-dioxane, this exercise demonstrated that the inclusion of facilities where these assumptions had to be made is unlikely to skew our conclusions from the assessment. So now we'll take a look at some of the new probabilistic and aggregate modeling approaches applied in the 1,4-dioxane supplement, on which EPA is seeking comment. These include down-the-drain modeling, probabilistic aggregate facility modeling, and the associated case studies to validate the approaches. These subjects are covered by charge questions 2.2 and 2.3. Recall that the underlying flow data and modeling methodologies applied in these analyses carry over from the facility-specific modeling updates where relevant, such as the incorporation of the NHD Plus version 2.1 flow line database and hydrologic information. EPA estimated down the drain loading to surface water using the EPA stochastic human exposure and dose simulation high throughput or SHEDS HT model. This model is a probabilistic model for assessing biologically relevant human exposures to chemicals and consumer products, which is based on the SHEDS multimedia model. The model includes information from activity diaries to define how products containing various chemicals are used. The exposure outputs from SHEDS HT were not applied in this supplement. However, the SHEDS HT model additionally calculates a distribution of daily per capita down the drain loading from the modeled usages, and that was used in this assessment. Product weight fractions applied in the model were updated based on information collected for this supplement. Representative values from the distribution of total per capita down the drain loading were selected for consumer uses and commercial uses. A general analysis was conducted to show the ranges of estimated average in-stream concentrations of 1,4-dioxane due solely to down the drain loading, and that's shown in the table on the right, which assumes no removal from wastewater treatment. Additionally, to validate the application of this approach to estimating down the drain loading, as well as the novel modeling framework that EPA developed to perform probabilistic and aggregate surface water modeling, these per capita values were applied in a series of case studies. When applied to the known populated areas in the case studies, the populations for census designated places were used, along with population proportions of occupations expected to be contributing to commercial uses of products, which were drawn from the Bureau of Labor Statistics. And to do that modeling, EPA developed a flexible modeling environment to handle the calculations of the probabilistic and aggregate pieces of the surface water analysis, called the eWizard model, and it was implemented in Excel as eWizard Excel. It's a steady state mass balance deterministic model in this basic form, and it includes modules for directly estimating down the drain loading, as well as including multiple direct and indirect releases and upstream background concentrations. The results include aggregated downstream concentrations and the relative contribution of each source. The base calculations follow the methodologies and decisions applied in the EFAS model for consistency across calculations. An R script wrapper for the Excel model was developed and called the eWizard XLR model in this arrangement. This scripting environment allows rapid automated model runs iterating through inputs, including drawing from distributions of inputs and collating results to perform the probabilistic release modeling presented in the 1,4-dioxane supplement. These next few slides describe the implementation of this probabilistic model as it relates to charge question 2.3. Here's a visual overview of the flow of data within that probabilistic eWizard XLR model as it was applied for the facility modeling. It was conducted as a Monte Carlo analysis, drawing 10,000 combinations per OES of facility release, hydrologic flow, and background concentration data as inputs to produce a distribution of possible in-stream concentrations at the point of release within that group of facilities. First, a facility within the group is selected at random, and within the facility, One of the available years of release amounts is selected, along with a random monthly average modeled flow for the receiving water body associated with that facility. Based on the Strahler stream order of the associated water body, a background concentration is randomly generated from distributions of monitoring data that have also been stratified by stream order. The monitoring data drawn for this model input for the background is from drinking water facilities that were assessed to not be located downstream from facilities releasing 1,4-dioxane, and they're thus expected to capture background concentrations derived from down the drain loading and other unreported releases, not industrial releases. These inputs are sent to the eWizard Excel modeling file, and the resulting concentrations are calculated and compiled by the R-script wrapper. This process is repeated 10,000 times per OES. The end result of that modeling then is a distribution as shown in some of the example results from the 1,4-dioxane application. And it's intended to be a more complete picture of the overall distribution of concentrations expected from releases aggregated with background data in each of the facility groups. And this is just a small subset of the probabilistic modeling results to demonstrate what the distributions look like. The full results for 1,4-dioxane can be found in the supplement in section 23134. This approach is contrasted with the facility-specific approach, which targets a high-end release scenario with a lower flow and presents more individual facility-specific results. In this particular application, because the concentrations due to industrial releases were much greater than those derived from background distributions, the inclusion of background concentration had minimal effect, particularly at the higher end of the distribution. And where monitoring data were available, EPA performed a series of case studies to validate the underlying eWizard Excel model, including its performance at aggregating multiple sources and estimating down the drain loading. In the most data-rich example, which is shown on this slide for Brunswick County, North Carolina, some of the inputs included were concentrations at the upstream boundary, release data for an industrial facility, direct estimation of down the drain loading from communities within the contributing drainage area, which is highlighted in yellow on the map. Sorry, jumped ahead there. Because multiple years of data were available for this location, including monthly upstream concentrations, multiple years of release data, and multiple years of monitored ranges at the downstream endpoint, a time series of results was able to be assessed. Due to the methodology applying average hydrologic flows to releases calculated from an annual total, and the surface water modeling and the surface water flows derived from the NHD Plus data set, this approach tends to target average in-stream concentrations. In this visualization of the results for this case study, the blue circles indicate modeled concentrations at the downstream end of the model at approximately monthly snapshots, which is based on the available input data. The brown line represents the mean concentration reported from observations at that downstream end, and the shaded area represents the full range from the minimum to the maximum. Overall, the results showed good concordance with the monitored concentrations, which supported a higher confidence in the modeling methodology and the assumptions representing reality. The next few slides address the downstream tracing analysis that was applied to the facility-specific modeling to evaluate how concentrations from industrial releases may change before reaching intakes to public water systems that draw surface water to distribute as drinking water. This information is relevant to charge questions 2, 4, A, and B, which refer to the downstream tracing methodology and how the dilution factors are applied to calculate estimated downstream concentrations. The downstream tracing analysis utilized the flow sequence data from the NHD Plus flow line network to allow automated downstream tracing and searching from points of release. This required associating points of release with NHD Plus reach codes as previously discussed, and also associating intake locations with NHD Plus reach codes. using geospatial analysis to identify the nearest reach. Where an intake was located on a larger water body like a reservoir, the reservoir was first associated with the flow lines crossing through it to include them in the downstream search. Once a downstream intake has been identified, a dilution factor is calculated by the ratio between the modeled mean annual discharge of the downstream and upstream locations, the intake and the point of release. This simple estimation of decrease in concentration as a chemical release moves downstream assumes that dilution is the primary driver of changes in concentration. While this assumption is shown to be a reasonable assumption for 1,4-dioxane due to its properties, for some chemicals, other factors may become more relevant in determining the fate of the contaminant in surface water. The calculated dilution factors are a very location-specific variable. The result of this dilution analysis is then reported as the diluted concentration at the intake as a percent of the initial concentration at the point of release, so that 100% would represent a downstream concentration that's the same as the upstream concentration, and 1% would represent a downstream concentration that is 1/100th of the initial upstream concentration. Here's an example histogram of dilution data from facilities in the 1,4-dioxane supplement with an estimated adult lifetime cancer risk found to be greater than 1 in 1 million at the point of release in the facility-specific modeling. In most cases, the downstream concentration is diluted to less than 10% of the original value at the point of release, while in some cases, releases may reach drinking water intakes with very little dilution. Due to the site-specific nature of this approach, where the same public water system is found to be downstream from multiple industrial release sites, those diluted concentrations can be aggregated as well. There are some assumptions and limitations inherent in this simplified approach, in addition to the assumption that the only decrease in concentration is due to dilution. Another assumption is that the stream discharge will always increase as the contaminant moves downstream. This assumption is generally true and holds up over relatively short distances as tributaries and surface runoff contribute to greater discharge. However, in areas with dams or other structures restricting flow or substantial water withdrawals, this assumption can be incorrect. And in those situations, basing the dilution factor on the discharge could overestimate the resulting downstream concentration. So at the very least, this is an upper bound on what that downstream concentration is. And EPA applied these dilution factors in two different ways. EPA explored a generic dilution approach by calculating the arithmetic mean of all of the dilution factors found for the facilities discussed in the previous slide, which was 1% of the initial concentration at the point of release. By applying this dilution across all releases, EPA considers a less location-specific application of dilution, which does not rely on specific intake information downstream of every facility, and could include situations with intakes not included in EPA's database, including where future development leads to additional drinking water intakes in new locations. Due to the linear nature of these risk calculations, the resulting risk estimates are also 1% of the initial risk estimates, and they're shown in these histograms presented on the slide. A site-specific approach focused on the intakes for public water systems located downstream from facilities where the facility-specific modeling found adult lifetime cancer risk greater than 1 in 1 million at the point of release. Surface water intakes were identified for 73 unique public water systems downstream from these facilities within 250 kilometers. The specific dilution factor for each respective location was applied based on the ratio of the mean annual modeled flow at the downstream point versus the point of release. And after applying the dilution factors to the concentrations and calculating adult lifetime cancer risk estimates, risk was still greater than 1 in 1 million for 20 of those public water systems. This approach can provide risk managers with more location and population-specific risk estimates where intake data are available. EPA noted in this analysis that many public water systems, particularly larger systems, can have multiple sources, sometimes coming from different water bodies or in combination with groundwater. This assessment only models concentrations for a specific water body and intake location and does not consider additional mixing, dilution, or treatment. So now that we've walked through each of the novel methods we use to evaluate the surface water pathway for 1,4-dioxane, I want to remind you all of the various methods of how they were applied to tell an integrated story in the broader context of 1,4-dioxane. So I'm going to wrap up with a high-level reminder of what we did and what we found for the surface water pathway. So we used several evidence streams and sets of analyses to evaluate risks from drinking water sourced from surface water. First, we considered surface water and drinking water monitoring data, as there's a pretty sizable monitoring data set. If you focus on finished drinking water results, which are shown in the figure, 11% of samples detected 1,4-dioxane. We only expect cancer risk greater than 1 in 1 million in the highest concentrations detected, which are indicated with the orange circle. So in most of the monitoring, 1,4-dioxane isn't even present above the limit of detection, but there may be particular locations reflected in that upper tail of the distribution where exposures and risks are higher. However, these monitoring efforts were not targeted to reflect TSCA COUs, and in most cases were found to not be co-located with industrial release sites evaluated in this assessment. These monitoring data align with the general pattern of modeling results in that they show a wide range of surface water concentrations, with some less frequent instances of relatively high concentrations. Because the monitoring data isn't necessarily targeted to evaluate concentrations at the specific locations where 1,4-dioxane is being released, most of our exposure and risk estimates rely on modeled concentrations. We've discussed several components that make up our water modeling analysis. We estimated concentrations resulting from individual sources on their own and in aggregate. There's the individual facility release modeling using a method similar to Fenceline with the updates described in this presentation. And we evaluated down the drain releases of consumer and commercial products. The general down the drain analysis is not site specific, but rather we focus on estimating what risks would be under a set of plausible conditions related to the size of the population contributing to releases and the size of the receiving water body. We also evaluated hydraulic fracturing releases, which was not discussed directly in these slides so far, but this assessment used the probabilistic modeling approach with distributions of releases to surface water calculated by the Monte Carlo approach described in the engineering section. Similar to the down the drain analysis, the assessment was not site-specific, but we estimate concentrations and corresponding drinking water exposures across a range of modeled releases. Then, as described in these previous slides, the probabilistic aggregate model was applied to expand on the individual facility release modeling by also accounting for other sources of 1,4-dioxane that occur upstream and present distributions of potential receiving water body concentrations on a per COU format. As discussed in the previous slides, where we did have monitoring data co-located with modeled water concentrations, we explored a couple of case study locations to compare model estimates to actual monitoring data and found strong concordance between modeled concentrations and monitoring data for 1,4-dioxane, increasing our confidence that the modeling approach does a decent job of predicting actual concentrations that occur in surface water. This slide highlights the elements of the analysis that resulted in cancer risks estimates greater than 1 in 1 million for modeled drinking water exposures for the general population. The overall take-home here is that each of the sources we considered contribute to cancer risks greater than 1 in 1 million under some conditions, either alone or in aggregate. For example, in estimating cancer risks from individual facilities summarized in the first bullet, we estimate cancer risk greater than 1 in 1 million for facilities associated with all COUs. We estimated risks under a range of assumptions about the degree of additional downstream dilution that could occur between the point of release and downstream intake locations. But even when accounting for that additional downstream dilution, as summarized in the second bullet, cancer risk estimates based on concentrations modeled at the point of drinking water intakes are still greater than 1 in 1 million for 20 out of the 73 public water systems evaluated downstream of releases, which serve a combined population of over 2 million people. We also saw cancer risk estimates greater than 1 in 1 million for some plausible conditions related to down the drain releases alone and at the high end of modeled releases from hydraulic fracturing waste. And of course, when you put it all together in the probabilistic aggregate model, we do see cancer risk estimates greater than 1 in 1 million under a range of scenarios. The potential relative contribution from different sources varies under different locations and considerations and is likely to be very site-specific. In some locations, risks could be driven entirely by high-end industrial releases, but even in locations with no industrial releases, down-the-drain releases have the potential to contribute to cancer risk greater than 1 in 1 million under some conditions. And as indicated by a lot of the monitoring data, we don't expect risk at all in many locations. Taken together, this set of analyses define the conditions under which different levels of risk may occur, both from individual sources and aggregate sources combined. To wrap up the surface water section of this presentation, let's broadly recap the strengths, uncertainties, and limitations that have been touched on across the presentation. The underlying methodology for the modeling for combining release and hydrologic data is robust and has been applied and reviewed in previous TSCA risk evaluations. Updates to the input data sets and expansions on the baseline monitoring framework, including the addition of NHD Plus data and development of the eWizard modeling framework, have allowed EPA to assess exposures where only probabilistic input data are available, such as in the down-the-drain and hydraulic fracturing scenarios, and also to extend the modeling to address downstream concentrations in drinking water source water. Where relevant monitoring data are available, EPA has found strong concordance with modeled concentrations produced by these methods. Of course, the quality of the modeled results are dependent on the quality of the input data, and in some cases, release and receiving water body information were less certain. Overall, outside of the case studies, there were limited opportunities to evaluate the methodologies with monitored concentrations of 1,4-dioxane that were co-located or temporally consistent with model results. This is especially true for the hydraulic fracturing and downstream drinking water analyses. Additionally, even when the downstream tracing methodology was applied to estimate concentrations at the point of drinking water intakes, this assessment did not include additional factors that could impact the concentrations in finished drinking water, such as mixing with other source water or treatment processes, because this information was not readily available. And next we'll move on to the groundwater exposure assessment.
Good afternoon. Thank you for joining. My name is Sean Shiflett. I am a physical scientist within the Office of Chemical Safety and Pollution Prevention. For this section of today's SAC meeting, I am going to be reviewing components of the groundwater exposure assessment. This assessment considers how individuals may be exposed to chemical substances in groundwater sourced drinking water using approaches novel to the TSCA Substance Control Act, or TSCA. This presentation will largely center around 1,4-dioxane, but may be applied in other chemical risk evaluations when scenarios support further investigation. To place this section into context with the rest of today's presentations and orient the SAC to this review as a whole, the next set of slides are related to questions outlined under Charge 3 on the land pathway. As I previously mentioned, this assessment is new and unique for existing chemical risk evaluations under TSCA. Groundwater contamination from disposing of industrial chemicals into different types of landfills is not always expected, but may occur when a landfill has aged out of its intended use, when there are perforations in the landfill's liner, or if the landfill is poorly managed during its lifetime and thereafter. In addition to these landfill characteristics, the chemical substance would need to possess unique properties like high water solubility, low volatility, and low biodegradability to support transport in groundwater. Additionally, the substance would need to be persistent in anaerobic environments. These traits are particularly applicable to 1,4-dioxane since there is a known history of groundwater contamination across the United States. In addition to this rationale, OCSPP has previously received comments on the need to expand risk evaluations to include all pathways for potential exposures. One of the many and most recent comments received was from the SAC final report on the screening level approach for assessing ambient air and water exposures to fence-line communities. As I quote, groundwater contamination may be extensive and the current screening process did not address this pathway either through water exposure or soil gas infiltration and vapor intrusion into homes and businesses. Consequently, fence-line communities that rely on private domestic wells may not be adequately considered as part of the screening process. Thus, this assessment is also partly in response to the SAC's request for more holistic assessments. Let's provide a little context about private drinking water wells. So fewer people across the United States rely on groundwater as their primary source of drinking water when compared to surface water. Approximately 15% of the American population use private wells to pump and supply their home with water for drinking, bathing, and other uses. Unlike publicly owned treatment works, these private wells are not subject to the Safe Drinking Water Act, and homeowners are responsible for ensuring the safety of this water supply. The challenge, however, is that these wells can become contaminated. The lack of monitoring for regulatory purposes and the potential for contamination support mitigating groundwater contamination as one approach to prevent human exposure from environmental contaminants. So let's start discussing monitoring data. Groundwater monitoring data for TSCA risk evaluations can come from many sources, but may be limited for many reasons. As seen on the map on the right, there can be substantial spatial heterogeneity in the data availability and concentrations. This can be due to the many potential sources of data or can be a result of little to no monitoring activity around facilities that have the potential for groundwater contamination. A challenge for this assessment was finding data specific to landfill monitoring. Many of the areas with 1,4-dioxane contamination could not be attributed to an individual activity, and in many cases were the result of historical uses of 1,4-dioxane. This lack of supporting monitoring data can lower the overall confidence risk evaluations may have in these types of assessments. Lastly, data source can influence how well groundwater contamination can be characterized. So let's transition to the modeling conducted for this assessment. We use the Hazardous Waste Delisting Risk Assessment Software, or DRAS. DRAS is not designed for TSCA-specific conditions of use, or COUs. It is a model developed by EPA regional offices to assess the risk of delisting hazardous wastes and disposing of them into non-hazardous waste landfills. DRAS relies on a probabilistic Monte Carlo assessment of source chemical, unsaturated zone, and saturated zone specific parameters to reflect national variation. It also utilizes a dilution attenuation scaling factor developed for the lifetime of landfills waste volumes ranging from 10,000 to 1 million cubic yards based on waste volumes encountered in EPA's Survey of Industrial Subtitle D waste facilities in the United States. So as I previously mentioned, DRAS is not designed for TSCA conditions of use, and we did not use the model for its intended purpose and are not suggesting that we would use the model for its intended purpose in future risk evaluations. This is because DRAS is intended to characterize the risk of delisting chemicals for disposal into non-hazardous waste landfills. This risk characterization is not limited to groundwater and does not directly provide a groundwater concentration. EPA used the weight-adjusted dilution attenuation factor, an output of the model, to determine what a groundwater concentration might be for a household within 1 mile of a municipal solid waste landfill. EPA then used hazard values from the 2020 risk evaluation and calculated a potential lifetime average daily dose based on the exposure factors handbook. So I want to wrap up with a summary of how we applied these methods in the context of 1,4-dioxane and what we found. For both disposal to landfills and disposal of hydraulic fracturing waste, we used the DRAS model to estimate groundwater concentrations that could result from these sources' varying conditions. In both cases, these are not informed by site-specific information, but instead focused on defining the bounds under hypothetical scenarios where we would start to be concerned about risk. Because we do not have much readily available monitoring data, it is less clear how well the upper bounds of these results characterize real-world scenarios. For landfills, we estimated groundwater concentrations that could result from poorly managed landfills under different combinations of landfill leachate concentrations and loading rates. Cancer risk estimates are greater than 1 in 1 million at the highest loading rates and the highest leachate concentrations. For hydraulic fracturing waste, again, we didn't have site-specific information on releases, so we relied on Monte Carlo distributions of modeled releases. We used those modeled releases to estimate groundwater concentrations, and then the lifetime cancer risk estimates start to exceed 1 in 1 million at and above the 95th percentile of the modeled releases. There is much uncertainty around the extent to which those exposure scenarios actually occur, but our analysis helps to define the boundaries where we would reach a given risk level. So now that we've walked through the monitoring data and the model data for this evaluation, we should spend a little time dedicated to the overall confidence in the exposure estimate. The overall confidence in drinking water exposure estimates resulting from disposal to landfills is low to medium. The modeling methodology is robust as it accounts for a wide range of scenarios. The release information relied on as model input data is supported by slight to moderate evidence, decreasing overall confidence. In addition, this drinking water exposure scenario relies on the assumption that groundwater concentrations estimated with the DRAS model may occur in locations where groundwater is used as the primary drinking water source. While the substantial uncertainty around the extent to which the exposures occur decreases overall confidence in the exposure scenario, this scenario represents a sentinel exposure. We think this is an important consideration given the wide range of characteristics that may drive how disposal of chemicals to landfills translate to chronic exposures to drinking water. With that, I thank you for your time.
Thank you very much. Very nice presentations by the EPA team there. So we are a few minutes ahead of schedule. We have a lunch break scheduled in about 15 minutes, but maybe 10 minutes. I think we have time for some questions before the lunch break. And this is, you know, we've heard a fair amount about water. So if you have questions, please, committee members and associates, please ask some of them now. And if you'll use the raise your hand function, we can see who you are with questions. Dr. Fox.
Hi, yes, Mary Fox. Excuse me. So I think this question is for related to the presentation Brian Groza provided, and it's around, I think it was around slide 61, and he mentioned updated flow estimates, and I think it's the modified hydrologic flow database, and I wanted to ask for a little more detail on that. So what does updated mean in this context? I mean, is there well, yeah, I'll we'll put it there for now.
Yeah, this is Brian Groza, and referring to the flow database as updated is versus previous applications for TSCA risk evaluations using the EFAST model with the reach file 1 flow database that I showed the comparison between.
Okay, so it's updated as to, but I guess can you give me more details on what was updated? Like what are the differences between what was done before and what you've done this time?
Yeah, so previously that reach file 1 flow database was used. So facilities had been associated with streams that were maybe higher order streams that were a little further away from the actual point of the facility. Whereas now with the more finer resolution database, we're able to associate the facilities with a better scale of those streams.
Okay, right. Yes, thank you.
Other questions? So, Dr. Heiger-Benes.
Yes, Wendy Heiger-Bernays. Thank you to EPA for presenting this and for providing a little bit more detail. My question focuses on background concentration. And I'd like a little bit more information as to where those data, the monitoring and the modeling come from and how they're being used. And this is in the surface water. So this may be Brian again, I don't know.
Hi, yes, this is Brian Groza, and the background concentrations as they were applied in the probabilistic modeling, is that what you're referring to?
Yes, that's correct. Thank you.
Yeah, those were collected from drinking water monitoring data from facilities reporting to either the UCMR3 or to individual state databases. And so that was raw or finished drinking water measurements. And those were used for locations that were analyzed to not be downstream from industrial releases or any of the facilities that are included in the monitoring, so there wouldn't be any double counting there. So these were locations where surface water was being used for drinking water with no industrial release upstream.
So these are no reported through your reporting systems upstream.
Correct. Yeah.
Okay. And the reason why you incorporate them was to separate what you're using as input parameters for the models, right? And are reflective not of what people are actually drinking, but of what is being contributed by the upstream release. Yeah, no?
Yeah, so yeah, they are to put the releases in more of a context, because if we're just analyzing the facility releases, those are theoretically being discharged to a water body that may have other concentrations of 1,4-dioxane from down the drain. And so to give some distribution to what the existing concentration in stream may already be if someone is going to drink that water. And as I mentioned, the relative contribution of these background concentrations was very low compared to a lot of the industrial releases. And that may just be because of the locations where we had drinking water available that were not downstream from industrial releases tended to have much lower concentrations.
Okay, and if I may, one additional question, and I think You touched on this, and this is about the updated modeling in terms of since in some cases you were assuming no dilution, if there were facilities that were, I'll say, close enough to influence a downstream reach point, how was that incorporated? Or are they each independent?
So there was the facility-specific approach where we looked,
Correct.
for each facility, how far downstream was a drinking water intake and what the level of dilution there was, and applied that dilution factor to that particular release so that we could estimate, what could actually be reaching that intake. So in those cases where either it wasn't very far downstream or there just simply wasn't much change in flow, so there was very little dilution from that point of release to the point of the drinking water intake, then there wasn't much change in the resulting risk calculation if you were to look at the point of release versus at that downstream point.
Okay, thank you.
Thank you. I think next was Dr. Ginsburg.
Hi, all. Gary Ginsburg. So I was struck by, when looking at the case studies and the overall data sets being used for this assessment, by the lack of POTW information, either in the case studies, there's census data that informs how much down the drain release there would be for a certain basin and river, but the location of POTWs in that space was not indicated. I didn't see anywhere in the supplement where POTW data are presented, which would give us a little bit more, I think, ground truth on down the drain releases if one knows about the population feeding into that wastewater collection area. And you may also know about some industrial sources and their processed waters, and whether, what kind of volumes they're releasing. So I think that there's a lot of potential information coming out of POTW discharge data, and you don't have to look very far. I mean, there's the case study you did talk about along the Cape Fear River in Brunswick, North Carolina, but there's good POTW information on the Haw River right next, right in that same basin, showing discharges. I don't want to pick out towns and intakes and outputs, but there's a lot of information there on POTW releases, and that I think would help inform the surface water pathway. I didn't see that in here, so just wondering about that.
Yeah, this is Brian Groza again. Thank you for that comment. We are interested in that kind of POTW data as well, particularly the population contributing to a POTW, as well as paired monitoring data would be very interesting to us to verify these approaches. And yeah, we'd be very interested in sources like that.
Well, and I'll just add that in these modern times of wastewater surveillance, for COVID variants, for chemicals of various types, whether it's PFAS or agents of personal use and abuse, that rivers are being monitored for. We know a lot about sewer sheds and how much population, and whether it's coming from dormitories. I've done some of this work in New York State, where we get a bit of a granular handle on these flows, And not saying that EPA should be, going way upstream and looking for dioxane concentrations here, there, and everywhere within a particular sewer shed, but I think that that is possible or potentially possible through additional monitoring to get that information, but at least at the main discharge point into something like the Haw River, where there is a lot of data on some of those POTWs, you could at least start there at the downstream end of the POTW.
Yeah, thank you. Any information to assist with further case studies to refine the methods would be of interest.
Okay, thank you. Dr. Rubin?
Hey there, Rainbow Rubin. I believe this question is also for Brian about the flow line data in identification of the nearest neighboring NHD flow line in the case that the reach code is missing. Just a point of clarification, when selecting the closest flow line, I'm just clarifying that the closest flow line from within the watershed is selected.
Hi, this is Brian Grosett, and can you clarify, you said within the watershed, so whether we map the facility to a watershed first and then identify a flow line?
In the case that the reach code was missing and the closest flow line was selected, just clarifying that that was within the watershed.
Yeah, we did not analyze the watershed that it was in. We just did a nearest neighbor spatial analysis for the nearest flow line connected to that facility, which is typically very close. There were some, we did expand that search up to 2 kilometers because in some cases the facilities were very large, and doing some deeper dive visual checks, that was an appropriate range to actually include the nearest one.
Great, thank you.
Okay, Dr. Potter.
Yes, thanks for the presentation. It certainly helped provide more depth to the documentation that we've been looking at over the last few weeks. I just wanted to ask sort of a generalized question that may drift into the policy area, so perhaps that may not be relevant, but I'm going to try anyway. There are other EPA programs where chemicals are regulated in natural waters, particularly under FIFRA, dealing with pesticides, where essentially modeling is the default approach to defining concentrations. And of course, over the years, and I've been involved in this in many ways, monitoring was recognized that there's plenty of data on it, but the granularity of modeling makes it extremely difficult to apply in a regulatory context. There was an interesting 2019 FIFRA meeting that dealt with this whole issue of using monitoring versus modeling data. So I just throw that out there that there are other ways of approaching the data, recognizing the agency's desire to use monitoring data, but looking at the monitoring data that was described in the documents, I have to say in general, I would find it to be unsatisfactory with large numbers of non-detects and lots of other issues. So anyway, I'd like to hear some thoughts on that. Again, maybe we're in the policy area, if so, we can save this for later discourse.
Was there a question for the agency there?
Well, I guess, okay, question would be to what extent would monitoring as opposed to modeling be utilized in a risk assessment?
Hi, good afternoon. This is Rochelle again speaking. So we would consider both modeling and monitoring data if it is available, and we would look at the data and determine whether it would be suitable for use in a risk evaluation and explain how it's appropriate or not appropriate for use. Is that the question that you're asking? Yeah.
Yeah, I maybe delving into policy issues, but I'm just expressing my concern from looking at the monitoring data that's available, that it really is very limited and does not really provide a rigorous support for risk assessment. Clearly, from my perspective, modeling provides a much stronger pathway to defining what risks really are.
Okay, so thank you. We are kind of past our time. Dr. Barakal, would you mind if we waited until after the lunch break to have your question, or do you really want to get it in now?
I can wait, although I have to say that my question is not about the water. So it's actually for something that was said before we started discussing water. So I don't know if it's okay that we discuss it.
If it is okay, if you do not mind, we will start with you right after lunch. Is that okay?
Sure.
And then Dr. Wright, I see that you're next, and I actually have a couple of questions myself. So maybe we'll pick up this question and answer period right after lunch, not to go too terribly long, but we'll go right after lunch with a few questions, and then the agency will get into the aggregate exposure and risk assessment portion of the presentation.
That's fine.
Okay. So I think with that, we're going to adjourn for an hour, and we'll be back at 40 minutes after the next hour. So here it's going to be 12:40. I guess it's going to be 1:40 Eastern time. Allah, is there anything we need to have for housekeeping before we go?
Well, we'll see you in an hour. Enjoy your lunches.
Thanks, everybody. Oh, welcome back, everyone. So I hope everyone had a good and maybe relaxing lunch. Probably some of you were working on charge questions. So we had a few questions related to the presentations. I'd like to ask the committee to please limit what we're talking about in this time frame to questions about the presentations or about the subjects related to the presentations. Specific comments that we have on the charge can come later when we're addressing specific charge questions. All right, so with that, I also need to say I received a chat piece of information from Dr. Ginsburg. I'm still getting through that. I'm not sure if that was supposed to be entered into the record, Dr. Ginsburg, or if that's something I'm not sure what that's for.
If you would like to share it, it will be part of the record. Or if
Yeah, sorry,
yes.
I thought I was sending it to everyone, then I realized it was only going to Dr. Cobb. So then I sent it to the EPA presenters because that was one of the tick options. But yeah, if you want to share it with all the attendees, I'm good with that.
Oh, okay. That's fine, and we'll make sure we get that in the record, and you can certainly speak to it during the comment period.
Yes, please. And if the SAC members need any clarification questions, please feel free to send them to me or to Dr. Cobb, the chair, and not to anyone else. Thank you very much.
All right. So thank you a lot. Now, I think we were at Dr. Barako.
Yes, and this is Dr. Baraka speaking. My question was, and this is going to be important for me also in terms of the charge questions I've been assigned. So during the presentation on the release information, I have to open the name. So I think this is a question for Rochelle and Frankly. It was mentioned that the monitoring data, a couple of times it was mentioned some comments regarding the monitoring data, and I wanted to have more of a better idea about what are the limitations that the EPA has regarding the TRI monitoring data, whether they think there is some sort of bias in some direction, whether the monitoring data is considered representative of what would be the population of release inventory. I would like to have a little bit more understanding about that. Is this an appropriate question to ask, or should it be asked?
No, that's a fine question there.
Video too. Hi, this is Franklin Hall. So if I understand the question correctly, I think you're asking about the part of the presentation where I sort of touched on our preference for monitoring data over modeling data, and that there are some limitations to the data that we get from programmatic databases like the toxic release inventory. And what that was really speaking to is the fact that only certain industry sectors have to report to TRI, and then on top of that, there is a reporting threshold that they have to meet before they have a reporting obligation. So where there are limitations to what information we can get from TRI, those are the places where we have to consider opportunities to model those releases. So I wasn't speaking to any bias related to the TRI data or release data in general.
Okay, and so I guess the follow-up question would be, when the data is available, meaning that it's above the threshold, can it be considered reliable data, the data that is provided? Or could it be their measurement error?
Well, so the data that's provided by TRI also is accompanied by what's called a basis of estimates. So facilities can provide a series of codes they can report that indicate whether or not their reported releases were based on engineering judgment, emission factors, site-specific emission factors, and as well as general emission factors. So there are a number of ways that can indicate the sort of the reliability of the data that they're reporting. We use TRI data because typically it's the best available data that we have with respect to reported releases for some of these conditions of use. So if we have better data, and we very rarely do, emission factors from industry or literature, then we will use that. But primarily, TRI is sort of the go-to. And there's some other databases that we also tap into, but TRI is the main one that we use for release estimation.
Okay, thank you so much.
You're welcome.
All right, and we had one more question from Mike Wright.
Yeah, this is for Franklin also. Can you hear me?
Yes.
I can, yep.
Yeah, I was struck by your statement that people who were defined as occupational non-users were not assumed to have any dermal exposure. if I've got that correctly. And it raised the question with me that I'd had before as I was reading through all of the documentation of how exactly you distinguish workers from occupational non-users. And in particular, I'm interested in the answer to that question with regard to maintenance workers who may have very intermittent exposures, but often when they are exposed, the exposure is really quite high. How do you handle them, and first and second, why the assumption that occupational non-users, however they're defined, have no dermal exposure? My experience is that if you've got a group of workers in a facility who are exposed, often everybody's exposed because the stuff gets on surfaces and in the air, and
So sure. So to answer the first part of the question, when I'm referring to the expectation that there would be no dermal exposure, it's relevant to 1,4-dioxane. We're really talking about volatile substances, right? So if there are particulates where situations where you might have settled dust in places outside of what you might consider the near field area, or the area where the primary workers who handles 1,4-dioxane is working, then there certainly could be dust that is carried over into areas where you might consider the far field, where non-occupational or occupational non-users are also working and may be exposed. But that's really only for particulate or solids. For 1,4-dioxane, we're not expecting that due to the volatility of the substance. In terms of distinguishing between workers and occupational non-users, if you still sort of consider the near field, far field framework, if you will, in considering the near field, the place where the workers are operating who handle 1,4-dioxane directly, and the far field being where the occupational non-users are located and who may be indirectly exposed to 1,4-dioxane. There are a number of different ways we can distinguish between those two worker populations. The primary way is to understand as much as we can about the activities of those different workers. And we get some of that data from the Bureau of Labor Statistics, where we can pull job classifications, job titles, and then their associated worker activities, and then distinguish based on our professional judgment and experience between those workers who are in the near field, who handle as a part of their regular daily responsibilities 1,4-dioxane, or involved in activities where you might handle 1,4-dioxane, and workers where their activities, as described by some of this data that I was referring to, would not handle 1,4-dioxane, but would certainly be in an area where 1,4-dioxane may be handled, and such may be, they may be exposed indirectly to 1,4-dioxane.
Could you answer about maintenance workers? Because at least in my experience.
Hey, Mike, can you hold on just a second? I'm getting a real bad ping on my audio from somewhere.
Yeah, there's a lot of pinging.
Can you hear me now? You still hear the pinging?
Yeah, I was hearing you, but there was a periodic ping and a high-pitched squeal.
Okay.
Seems to have subsided. So, Mike, if you go ahead.
Yeah, let me try again. My experience, at least in operating chemical plants, is you've got a lot of operations that take place in what are called closed systems, and people who are running those systems are often in control rooms, and if they're on the floor at all, they're usually monitoring things that are, again, enclosed. A maintenance worker, on the other hand, may only visit that area once every week to fix something. But when they fix something, the closed system suddenly becomes open, and their exposure is quite high. So how would you define them, as occupational non-users or as exposed workers?
So conventionally, maintenance workers are typically classified as workers, or as the primary workers, not necessarily an occupational non-users. And so I think what you're referring to are situations where you might have line breaks where there is equipment maintenance needed, change out of pumps, flanges, things of that nature. Those workers would not be considered to be occupational non-users. And this is sort of on a case-by-case basis, because we may understand certain activities that may change that classification. But primarily, we expect, even though the frequency would be much less than a primary worker, that a maintenance worker would be exposed to the concentrations that would be very different from an occupational non-user.
One final follow-up question. You described, I think, reading descriptions of what various groups of workers did during the day. Did you and your team have an opportunity to actually visit some of these facilities and really follow the course of the work over time?
Yeah, so we have not visited facilities as a part of this risk evaluation. At least I've not been part of any of those plant visits. But that's one of the things we're doing is we're reaching out, as I mentioned during the presentation, to stakeholders to get additional information that may be available, that may be unpublished, that we could use to improve our assessment.
Yeah. Let me just make one final recommendation, and that is that I hope that for future evaluations that changes, because I think you really can't understand exposure to the extent that, well, you can understand it to some degree, but your understanding becomes much more sophisticated if you can actually go and look at it, like with practically everything else in life.
All right, thank you. We do need to move on to the next presentations. I want to kind of give EPA a heads up. I have questions about the exclusion of the DAC Americas site from surface water data. And as a corollary, the statement that Liverpool, Ohio was considered a low-end scenario when that's the only monitoring data you have. I do have one specific question that maybe is in the documents that I just didn't have a chance to get to, and that's in slide 71 about the down the drain loading. Do you actually have measured data for that, or is that all modeled data?
Hi, this is Brian Groza, and for the down the drain loading, that is dependent on modeling primarily, not monitoring data.
Okay, I thought that was the case, but I wasn't sure, so I wanted to ask the question to make sure that that was all good. And so I think now we can move on to the aggregate exposure assessment. And I'd like to remind everyone, this is George Kopp speaking. I'd like to remind everyone that we do have time for questions, about an hour's worth coming up soon. So if we have more questions, we're able to ask them. But at this time, I'd like to invite EPA speaker for aggregate exposure and risk assessment. I'm not sure how to pronounce your name. Is it Vulemeyer?
Close. It's Villamir. Much better.
I'm sorry, that was pretty bad pronunciation.
No, you did a very good job compared to some I've heard. Don't worry. Okay. So good afternoon. My name is Kevin Villamir. I'm an exposure assessor in the existing chemicals risk assessment division. I'm going to present our aggregate exposure and risk assessment. While I contributed to the ambient air pathway exposure analysis, I want to acknowledge my colleagues Brian Groza and Susanna Wegner, who did the focused work on aggregate. I may defer to them on technical questions as appropriate as we get into the question and answer session. Okay. Here again is our charge table to guide us through these series of presentations. This presentation transitions to charge question 4, highlighted in orange. This is the final charge and relates to EPA's consideration of aggregate exposures. Here we provide an outline for this specific presentation. We begin with a discussion on aggregate in the context of TSCA. We will follow this up with a broad overview of the aggregate concepts EPA considered in the 1,4-dioxane supplement. Next, we'll shift the discussion to provide a brief update to the air pathway exposure analysis included in 1,4-dioxane. While we do have a specific charge on the air exposure analysis, we do not have a specific charge on the air exposure analysis. It does inform the air pathway analysis, the aggregate pathway which is why we're going to share that. We close out this presentation with a discussion on the air pathway aggregate analysis methodology, for which we do have a charge, and what EPA evaluated quantitatively and qualitatively in the 1,4-dioxane supplement. The TSCA statute directs EPA to describe whether aggregate exposures were considered and the basis for their considerations. Aggregate exposure is a combined exposure from a single chemical across multiple routes and pathways. In the 1,4-dioxane supplement, you can find EPA's discussion of aggregate and sentinel exposures in section 5.2.2.5. EPA considers several levels of aggregation in TSCA risk evaluations shown on this slide. The decision whether EPA pursues quantitative or qualitative considerations of each level of aggregation is based on chemical-specific considerations. EPA is still exploring which particular factors are most relevant and to the extent to which we pursue each level of aggregation. Our primary aim at this point is to clearly communicate our rationale for levels we do pursue and any uncertainties associated with our approaches in this 1,4-dioxane supplement. We are welcoming comment on this. Regarding levels themselves, let's start with exposure routes. Individuals or groups of individuals may have exposure to a chemical through one or more exposure routes. For example, an oral, dermal, and/or inhalation exposure. To consider aggregation across routes, EPA considers whether the risks from each individual route may be additive across another exposure route. For example, most of the occupational uses we evaluated in 1,4-dioxane result in exposure through both dermal and inhalation routes. So EPA considers whether the risk from dermal and inhalation routes may be additive. There may also be situations where multiple sources contribute to an individual's or a group of individuals, like a community, exposure to a chemical. In this case, EPA considers scenarios where multiple sources or facilities release the same chemical to air in the same local community, or release the same chemical to the same receiving water body or other pathways. The third aggregation EPA considers is across pathways, where a chemical release to different media may result in exposure to the same individual or group of individuals via multiple pathways. For example, exposure may occur through both air and water pathways. In the air and water pathway example, EPA needs to consider whether it's appropriate to aggregate across inhalation and oral exposure routes within the air and water pathways, respectively. The final aggregation EPA considers is across exposure scenarios. In this case, an individual or a group of individuals' exposure may co-occur under multiple scenarios, like occupational and general population or occupational and consumer exposure scenarios. Co-occurrence can also involve occupational, general population, and consumer exposures. In these situations, EPA considers the extent to which we have evidence that exposures and risks assessed for each of these scenarios individually may co-occur in some individuals or groups of individuals. Although EPA is still in the process of defining a consistent set of rules for determining how and when we consider each type of aggregation in the context of different chemicals assessed under TSCA, with each new assessment, EPA is making incremental progress and testing new approaches to consideration of aggregate exposure. Feedback received on our approaches, as applied in the context of specific chemicals, can help shape EPA's broader decision-making framework for considering aggregate exposures. For 1,4-dioxane, we considered each of the 4 levels of aggregation presented in the previous slide. In the 1,4-dioxane supplement, EPA focused on developing quantitative approaches to assessing aggregate exposures and risks resulting from multiple sources contributing to individual pathways. Specifically, EPA considered multiple facilities releasing 1,4-dioxane to water, and separately, multiple facilities in proximity releasing 1,4-dioxane to air. For the other 3 aggregate considerations across routes, pathways, and exposure scenarios, EPA used a qualitative approach. While we want to acknowledge the potential for these aggregate exposures, EPA determined there is a substantial amount of uncertainty around each, which leads to low confidence in any quantitative assessment of them. EPA therefore addressed these 3 considerations through a qualitative approach of the uncertainties, which I'll discuss a bit more detail in the presentation a little later. You already heard about the quantitative approach we took to estimate aggregate exposures and risks for the water pathway in the previous presentations by Brian Groza. Shifting focus, I'm going to take a few moments to talk about the air pathway exposure analysis, which informs the aggregate methodology. I'll then talk through the aggregate methodology EPA applied in the 1,4-dioxane supplement. The next two slides present an overview of the methodologies used to assess air exposures in the 1,4-dioxane supplement. These methodologies were previously reviewed by the SAC in 2022 and therefore are not subject to further review or a charge. However, this overview provides some brief context on the air pathway exposure assessment as a whole, so you generally understand what EPA did and from where the results we carried into the aggregate analysis came. EPA includes an assessment of general population exposures via the outdoor air pathway in this 1,4-dioxane supplement, because 1,4-dioxane is released to air and expected to persist in air. EPA applied the methodologies previously reviewed by SAC in 2022 to this 1,4-dioxane supplement, as a final report from SAC in 2022 acknowledged that the methodologies may be protective for the pathways included, which included the air pathway, but should consider multiple years of release data and aggregate exposures. As you will see in the next slide, EPA both applied the previously reviewed methodologies and also conducted additional analysis to include multiple years of release data and aggregate exposures in this supplement. This slide visually shows air exposure analyses EPA conducted for the 1,4-dioxane supplement. It highlights analysis methodologies that were previously reviewed by SAC, shown in peach and blue, as well as an additional analysis shown in green and orange, which expand the air pathway exposure assessment for this particular supplement. In summary, both the screening and single-year analysis methodologies were previously reviewed and therefore not subject to a charge. The multi-year analysis shown in green is an additional analysis added to the 1,4-dioxane supplement to expand upon the single-year analysis. However, although the multi-year analysis is an additional analysis, it applies previously reviewed methodology and therefore is also not subject to a current charge. For the multi-year analysis, EPA simply input more data that resulted in more information to be considered as part of the evaluation. Specifically, in the 1,4-dioxane supplement, we considered all facility-specific releases reported to TRI over a 6-year period, along with the facility-specific arithmetic average of those reported releases. The models used in these analyses are also previously peer-reviewed and thus not subject to any current charge. The models include AirMod, which is EPA's regulatory model for air, and IIOAC, which is a TSCA-developed model based on pre-run AirMod scenarios. These models are air dispersion models that consider facility-specific release amounts, meteorology, and other parameters, for example, physical static parameters, plume characteristics, and terrain, and others, to estimate chemical concentrations at different distances for both fugitive and stacked releases at the facility-specific level. The estimated chemical concentrations are then used to calculate exposure concentrations and associated risk estimates, which can be compared to relative benchmarks. Finally, EPA conducted an aggregate analysis shown in orange to consider general population exposures resulting from multiple facilities releasing 1,4-dioxane in proximity to each other. The aggregate analysis for 1,4-dioxane was specifically designed to use existing results from the single-year analysis for simplicity. The methodology EPA applied for the aggregate analysis is novel and thus is subject to a current charge 4A for the air pathway. With that overview of the air exposure path assessment, I'll now briefly present the aggregate methodologies for the air pathway. A detailed discussion of this aggregate analysis is included in Appendix J of the 1,4-dioxane supplement. The aggregate analysis EPA applied to this supplement consists of 3 steps shown on this slide. I'll discuss each step over the subsequent slides, but in summary, step 1, we map all the facilities reporting releases of 1,4-dioxane to the air. Step 2 identifies and groups facilities whose 10-kilometer or closer buffer rings overlap with another facility releasing 1,4-dioxane. Step 3 adds exposure concentrations and/or cancer and non-cancer risk estimates within each facility group, otherwise referenced in the supplement as aggregate facility group, at each distance evaluated to determine aggregate exposures risks. Let's begin with step 1. where EPA takes the release data and geospatial information, including latitude and longitude, reported to the Toxics Release Inventory, or TRI, and maps that information using ArcGIS. This provides a national map of 1,4-dioxane releasing facilities as shown on the slide. With the release data, geospatial information, and this map, EPA can identify where facilities appear to have overlapping buffer rings with other 1,4-dioxane releasing facilities. Step 2 has 3 components. First, EPA identifies where we may have groups of facilities with overlapping buffer rings. For 1,4-dioxane, these are identified by the 5 larger circles on the national map. Second, EPA zooms into those proximal facilities to verify an overlap occurs and to identify the entire group of facilities with overlapping rings as shown in the inset map on the right. Third, all facilities within a given group with overlapping rings are placed into an aggregate facility group for further analysis of the aggregate exposures and risks. Steps 1 and 2 of this aggregate approach primarily consists of data mapping and manipulation, and therefore has little to no uncertainty beyond potential uncertainties with the underlying reported data. Step 3 is where EPA calculates the aggregated risks using the 2 equations shown on the bottom of this slide. For the 1,4-dioxane aggregate analysis, this step involves several components to get the individual facilities aligned to allow a simple but direct aggregation of risks. First, once the aggregate facility group is formed, EPA aligns each facility within the group as if all are releasing 1,4-dioxane from the same point or centroid. This is accomplished as shown in the series of diagrams under the first bullet. In these diagrams, the green dot represents the release point of each facility in the group. In this example, there are 4 facilities. The dashed rings represent the buffer rings at a select few distances from the release site that we modeled. EPA actually modeled 8 finite distances and 1 area distance for the single year analysis. There's actually 9 dashed rings that will align through this action. Next, EPA identifies the overlapping facilities and virtually lifts them off the 2-dimensional map into a 3-dimensional space. EPA then shifts the facilities into a theoretical stacked configuration where the release points from each facility align at a single centroid position. Finally, EPA adds together each facility's risk estimate at each distance evaluated to get an aggregate risk. These aggregated risks can be compared to relative benchmarks to see any impacts on potential risks due to aggregation. Before transitioning back to the broader aggregate discussion, I wanted to share some concluding remarks around the specific air pathway analyses included in this supplement. Generally, general population exposure assessment in this supplement is not subject to a specific charge to this SAC panel. The methodologies utilized were previously reviewed by SAC in 2022 and is provided for context to inform the air pathway aggregate analysis. The air pathway aggregate analysis is subject to a specific charge, charge 4A, as it applies a novel methodology to aggregate exposures and/or risk estimates to inform general population exposures resulting from multiple facilities releasing 1,4-dioxane in proximity to each other. SAC's feedback on the methodology presented, along with alternative improved approaches, can help inform EPA's future air pathway aggregate assessments. With these concluding remarks, let me transition back to the broader aggregate discussion to close out the presentation. Now that you've heard a bit more about how we approached aggregate for the air pathway, in these final few slides, we come back to close out the broader considerations of aggregate exposures by EPA in the context of 1,4-dioxane to inform your discussion of charge question 4 on aggregate exposures. As we just discussed, and as you heard in the presentations on water, EPA quantitatively evaluated aggregate exposures in the context of multiple facilities impacting general population for both air and water pathways individually. The remaining 3 elements identified in this slide were only qualitatively assessed in this 1,4-dioxane supplement. The 2 images on this slide revisit the quantitative aggregate analysis EPA conducted for both the water pathway, which is on the left, and the air pathway on the right. For the water pathway, the team developed an aggregate model to estimate water concentrations and corresponding drinking water exposures and risks that result from multiple sources of 1,4-dioxane in surface water. This approach considered highly spatially resolved flow data, drinking water intake locations, and monitoring data, specifically finished drinking water monitoring data. This analysis evaluates aggregate risks across multiple facilities discharging to a common water body. Your feedback on charge 4B can help inform EPA's future refined aggregate water exposure assessments. For the air pathway, EPA considered aggregate exposure and risks from multiple industries, industrial facilities in proximity within 10 kilometers or 6.2 miles from another releasing facility. EPA took a conservative approach by layering exposures and associated risks over the same spatial overlap. Additionally, analysis of aggregation for the air pathway in the 1,4-dioxane supplement was not pursued because the findings from the initial analysis did not change the overall risk conclusions. Generally, one releasing facility contributed to most, if not all, of the risk within a given aggregate facility group. However, for other chemicals in the future, this may not be the case, and refinement of this approach may be appropriate. Your feedback on charge 4A can help inform EPA's future refined aggregate air exposure assessments. EPA qualitatively considered the potential for aggregate exposure and risk across exposure routes and pathways. We discussed the potential for these aggregate exposures and the uncertainties around them in section 5.2.2.5. Our approach for the qualitative aggregation is the subject of charge 4C. To summarize, EPA considered whether to aggregate cancer risks across inhalation, oral, and/or dermal routes of exposure, but there is uncertainty around the extent to which cancer risks across routes are additive for 1,4-dioxane. Liver tumors are the primary site of cancer risk for oral exposures. Inhalation exposure in rats is associated with multiple tumor types, including liver. The IUR used to calculate inhalation cancer risk reflects combined risks from multiple tumor types. It is therefore unclear the extent to which it is appropriate to quantitatively aggregate cancer risks based on the IUR with liver tumor risks associated with oral and dermal exposures. EPA describes this as a source of uncertainty in the 1,4-dioxane supplement. EPA considered aggregating risk across pathways because people come in contact with drinking water and air pathways through different routes of exposure. The decision to not aggregate across routes means we also didn't aggregate across those pathways. EPA qualitatively considered the potential for aggregate exposure and risk across exposure scenarios. EPA considered aggregate exposure and risks across exposure scenarios, for example, occupational and general population. However, EPA does not have and did not identify through our systematic review process specific information to inform our understanding of these or other potential multiple combinations of exposures that could occur. For example, EPA did not identify information on how many workers and/or ONUs in a specific releasing facility also live within 6.2 miles of that facility or another facility releasing 1,4-dioxane, and also use a specific consumer product, either commercially or at home, which contains 1,4-dioxane, resulting in a consumer exposure. Additionally, given the levels of risks we are finding for 1,4-dioxane at the individual scenario level, either occupational or general population or consumer, EPA does not expect aggregating across scenarios will change the overall risk characterizations or overall conclusions reached. Therefore, EPA qualitatively acknowledged that some individuals or populations may experience aggregate exposure from both occupational and general population scenarios, but does not quantitatively assess such aggregation. And I will close out. We'll take any clarifying questions that you may have.
Thank you. So, Dr. Apti?
Yeah, hi. Thank you for that really nice presentation. Just to get this point one more time clear in my notes. In the last point, you said that EPA did not aggregate the risk across multiple scenarios, but EPA does acknowledge the possibility of that in qualitatively, but quantitatively cannot do that, right? That's what you're saying?
Yes, it is. Basically, to even any kind of quantitative analysis, you'd require to get some information that can inform how many workers at a particular facility also live within the distances we evaluated of that facility or another facility. Plus, you need to see if they consider consumer scenarios and so on. So that's why we qualitatively express it in this supplement as a qualitative rather than a quantitative assessment.
And does that leave it open for a future, some point in time analysis where such data would be available, where you could actually turn the qualitative assessment into a proper quantitative assessment?
Oh, if we can get some data that can inform that, we would love to see that information, see how it can inform us, right? If you have knowledge of some information that may be out there, that could be definitely beneficial to share, and we can look at it and consider it as long as there's reasonably available information.
Right, great. I just wanted to bring that point out because we are also informing researchers from this on the go about the lacunae we have in the data. And this could be one of the places where people could think about it. So thank you for that comment.
You're still on mute if you were speaking.
George, I got a question.
Sure. Dr. Portier, go ahead.
Back on the slide where you show the stacking, I think it's like 113, 114, something like that. Okay, yeah, no, previous. Well, yeah, that one, either one, that one or the picture. So if you look at the left-hand image, you have 3 sites identified as being within your focus areas, but really no 2 sites overlap. I mean, only 2 sites overlap at any one point, but you define all 3 as a group. So you're allowing this kind of linkage. If 2 overlap, you see the question I'm asking. I'm just wanting to make sure how you're defining the exposure group. To my way of thinking, I guess I would have expected all 3 to overlap with each other, and that would be a group. Here I'd have 2 groups. The top 2 would overlap with each other, and the 2 right ones overlap with each other, so that anybody living within those areas are only going to be exposed to 2 out of the 3 facilities, releases from 2 out of the 3 facilities. So what's the thinking of kind of bringing them all together? George, you're looking confused.
I'm simply listening. That is my listening face, Ken.
Oh, okay.
Sorry, we were on mute.
There we go.
There's actually 4 facilities in this group. You can't see from this image, the one in that middle group is actually 2 facilities that are literally like almost right on top of each other. So that's why we have 4 facilities, not just 3. But to your point, you're correct. If you want to label these A, B, C, and D going from left to right, facility A overlaps at maybe, let's just say, keep it easy, around 5,000 to 10,000 meters, right? Those are the outer rings. They overlap only there, but they don't overlap inside. And then facility B and C in the middle overlap with facility D in the lower right. But you're right, A and D don't overlap at all. They don't touch. So someone in A is not going to be exposed to D. However, when we did the aggregate as a more conservative, more health protective approach, we combine them as if they're emitting from the same point. So it does pull facility A and facility D on top of each other. And it gives an impression that they could be exposed to all of them. But your point's well taken. There's not actually an overlap there. But for simplicity in aggregating it, if there's any overlap and interconnection, we combined all of those together in a single facility group. And then we would aggregate all those exposures together at the individual distances we evaluated. But your point is well taken that you don't actually have overlap in A and D, but we still include in the same group. It's a little more conservative and it's more health protective. And as we saw with the results, and we mentioned in the last slide, it still didn't change the overall findings even from the individual facility analyses that we did. But it is a more conservative approach.
Have you looked at anything other than the 1,4-dioxane facilities? I just wonder, when you apply this more generally, to say where the industries are more geographically clustered. And I'm thinking petrochemical plants or something like this. You know, you could end up with 20 or 30 facilities, right? I mean, is your methodology going to be able to handle that growth for some of these industries? I mean, this is pretty spread out, so you only have 3 or 4 cluster groups, right, to deal with.
Yep. Yeah, the more facilities you have, the more information you have, it you do have bigger groups of facilities. Petrochemical plants, they overlap with multiple processes in a single facility too. So, but you're correct, as you get more data, we would, again, input like that we can look at and how we might improve or other things we might want to consider in building this group. This was specifically designed for simplicity and with the 1,4-dioxane chemical in mind. And as you noted, the facilities releasing this are relatively limited. You have some other chemicals that have hundreds of thousands of release points. Are you going to add them all together? Yeah. So I hear you.
Thank you.
Okay, so we're back to Dr. McKenzie.
Yeah, so kind of, thank you for that presentation. And I kind of have a question that relates to what Dr. Portier was getting at. So when you consider the hydraulic fracturing sites or oil and gas development sites around the country, which are very dispersed, were they included in this aggregate calculation for air exposures? And are you intending to do that?
We're playing musical chairs.
Yeah, I'm gonna pass it.
Right.
I'll pass it on to Brian. He did a lot of the overlay and the combining of these facilities. So.
Did we lose the EPA folks?
Hi, this is Brian Groza. Just to answer that, this was only applied to the industrial facilities, this method that's on the screen right now, and not to the hydraulic fracturing operations. And I just wanted to add to the response to the last question too, that this is sort of like a first tier assessment to identify these locations and check what an aggregated concentration and risk may be at these sites. And then where there are larger groups, or we identify some additional risk in that situation, then we would go back and do a deeper dive and say, okay, is this realistic considering the shape or the spread of these facilities, and go further from there.
Okay, thank you. I was just would add that some of the oil and gas development sites are becoming quite large and can be considered to be small industrial sites that are really very dispersed across the areas that are experiencing this development.
So thank you. Dr. Rubin, before you ask a question, I have a corollary to the last question, and to keep EPA from having to jump back and forth, I wanted to ask, I don't think I saw anywhere in this presentation where the discharge atmospheric release of 1,4-dioxane was considered from wastewater treatment plants, because in the previous SAC, we recognized and that the EPA was assuming that the majority of the 1,4-dioxane was being released in the atmosphere or being sequestered in things like sediments. So were those point sources considered in this assessment or not? Sorry, while we're waiting on the response, that was me, George Cobb, speaking.
Right, this is Brian Groza. That was in the 2020 risk evaluation. We did not revisit what was in the 2020 risk evaluation.
So you're saying you did not take the SACC recommendation to revisit that while you were doing this?
That's correct.
Okay, thank you. And now, Dr. Rubin, sorry for jumping ahead of you.
No problem. Go right ahead. Rainbow Rubin, thank you for the presentation. Can you tell us more about how you made the decision not to aggregate across pathways, air and water, instead of air or water, considering cancer effects on the liver for both air and water? And wouldn't it be preferable to introduce uncertainty from a more conservative approach of protecting the liver rather than uncertainty introduced from not aggregating pathways? Thank you.
Yeah, this is Susanna Wegner. I'm a toxicologist and the assessment lead on 1,4-dioxane. Thanks for your question. Effectively, I mean, I think the way Kevin described it is the rationale that we applied, right? That there is uncertainty, and therefore it would be difficult to lean into any quantitative numbers as the basis for a regulatory action. But we do think that there's some additivity there. We just don't know exactly what the quantitative relationship looks like. And so we address it qualitatively because we think it's important. We also acknowledge that there's a pretty substantial uncertainty in exactly how those the exposure across routes would be aggregated. That said, you were asking about pathways. You know, if we do not aggregate across inhalation and the oral and dermal exposures, then there's not much we can do to aggregate across air and water because those are through different routes. Does that make does that make sense?
Yes, thank you.
Yeah, thanks.
Okay, thank you. So, Dr. Apte, you have a question?
Yeah, I just wanted to make sure that I understand this. When you say substantial uncertainties, you're basically saying lack of data, right? And that is what the uncertainty is.
So it's not so much lack of data, really. The going back to the 2020 risk evaluation where we presented all of the hazard assessment, the oral cancer risk is entirely driven by liver tumors in the rodents, while the inhalation cancer risk has contributions from multiple tumor sites. And our current approach is to focus on aggregating only when we have a shared target organ. So in this case, we don't have a lot of, the source of uncertainty is uncertainty around the degree to which the quantitative estimate for inhalation is driven by liver versus other tumor locations.
Okay.
So it's not that we don't have any information, it's more that we just aren't sure exactly the relative contribution across tumor types.
Okay, I get it. Thank you.
Yep.
All right, and then we have one final question from Dr. Ginsburg.
Yeah, sorry if this already came up. I had to step away for a minute, but I was curious about the decision to just model cancer risks according to a 33-year adult-only scenario. We know that we know that in a public water supply that may be many thousands of people drinking the water, that you can be exposed to the water as an infant, young child, through various stages of water intake per body weight ratios, and if you have 33 years of exposure, it may well be as 18 years as a child, or at least the first 6 years, where the exposure ratios are much different than in the adult setting. And that would add to the, if out of those 33 years, 6 of them, for example, which is a fairly common approach.
So Dr. Ginsburg, we need to limit this to questions. Do you have a question?
Yeah, so why did EPA analyze the additive or the aggregate of childhood plus adult exposure in an aggregate risk?
So for the water pathway for oral exposure, we looked at 33 years. 33 years is I think it's the upper bound, 95th percentile residential time in a given home, and from the exposure factors handbook. And what we did is we looked at what the risk would be for 33 years starting from birth, and we looked at 33 years as an adult. And if this were a different chemical where we had age-dependent adjustment factor, those 33 years from birth would really be driving cancer risk. In the case of 1,4-dioxane, if you average across 33 years starting from birth versus 33 years only in adulthood, your relative exposure is actually higher as an adult, because you don't, in the sort of middle duration of childhood, you have a bit of a dip relative to body weight. So actually it's the 33 years as an adult where we see the highest exposure relative to body weight occurring consistently for 33 years. This is all stuff that we would welcome your input on, both in terms of the exposure duration that we look at and the assumptions that we land on for exposure factors. I'd love to hear from Zach on any of that.
Can I just ask, is that analysis in some appendix or data table for the years from birth versus the years just as an adult?
Yeah, so in the supplemental files, in the Excel, I believe it's called the risk calculator for the surface water pathway, and the groundwater pathway as well has the same underlying assumptions. And then I believe the appendices related to our exposure calculations also have not as granular information, but provide a summary of that. And then I'll say for the air pathway, we also assume 33 years, but there's not an age dependency in the same way in this case.
Right. Thank you. And Dr. Wegner, I need to beg your indulgence for just a second, and everyone, we're all suffering through the trials of a new chair here. I forgot to call the roll after lunch. So I need to do that pretty quickly. So if you'll please just bear with me. And it just, yes, I'm here or something like that is fine. Dr. Apte?
And
Yes,
I forgot to remind you, I'm sorry.
Do not worry. You've got lots to do. Dr. Baker? Dr. Chasen? Oh, I see you. I'm here. Dr. Ike?
I'm here.
Dr. Fox?
Here.
Dr. Graham?
Here.
Dr. Heiger Bernays, I see you there. Dr. Jenkins?
Here.
Dr. Marcette Nieves?
Great. Here.
I'm getting there. Dr. Messerling? Not here. Dr. Ottinger?
Yes.
Dr. Presbilla?
Present.
Dr. Rife?
Yes.
Dr. Rubin already asked a question. Dr. Rumpler? Dr. Rumpler? Did Dr. Voorhees join us? Mr. Wright?
I'm here.
I think I heard, yes, you asked a question. Dr. Bennett?
I am here.
Thank you. Dr. Barakal asked a question. Dr. Clark?
Here.
Dr. Ginsburg asked a question just now. Dr. Henneman? Dr. Henneman?
I think he's out in the afternoon.
Okay. Dr. Jajak?
Here.
Thank you. Dr. McKenzie asked a question. Dr. Miglindo?
I'm here.
Thank you. Dr. Portier asked a question, and Dr. Potter?
I'm here.
All right. Okay. Thank you for responding there and letting me jump in there. So now we're ready for the presentation by Dr. Wegner.
Great, thank you. All right, you should be able to see my screen. So, oh, no, I need to reshare my screen. All right. Okay, so my name is Susanna Wegner. I'm a toxicologist, and I was the staff level assessment lead for the 1,4-dioxane supplement. And you've just heard about the novel approaches that we applied throughout the 1,4-dioxane supplement. And now I have just a few final slides to briefly remind you how it all fits together in the context of the supplement. So I'll start with just a quick reminder of the scope of the supplement. To address the critical gaps of the 2020 risk evaluation, the supplement evaluated risks from exposure pathways that had not previously been assessed for 1,4-dioxane. Specifically, those include occupational exposure to 1,4-dioxane produced as a byproduct in industrial processes or present as a byproduct in commercial products, and general population exposures either through drinking water from surface water or groundwater or through air. Now, we've focused our presentations today around the charge questions we've posed to the SAC on novel methods that we've applied throughout the assessment. And you've seen the summary table throughout the presentations. It highlights the sections of the 1,4-dioxane supplement where we applied each of those new methods that we're asking for your input on. But those charge questions do not capture the full scope of the supplement. And so I want to remind you of what the full document looks like and how the novel elements you're reviewing fit into it. And this figure from the introduction of the supplement provides a roadmap for the document and illustrates how the release assessment, exposure assessment, and hazard assessments from 2020 all inform the risk characterization for both occupational and general population exposure scenarios. And I'm going to use this to highlight where the methods that are the subject of the charge questions were applied in the context of the supplement. So the methods that we're requesting feedback on in charge question 1 are applied in the release assessment in section 2 and the occupational exposure assessment in section 3. And the methods we're requesting feedback on in charge question 2 are all focused on methods for estimating surface water concentrations. And in the supplement, we apply those methods in section 2 where we estimate water concentrations. Then those estimated water concentrations feed into our drinking water exposure estimates in section 3. The methods we're requesting feedback on in charge question 3 are intended to estimate groundwater concentrations that could result from releases to land. In the supplement, we apply these methods in section 2, where we estimate groundwater concentrations. And as with the surface water, those estimated water concentrations then feed into our drinking water exposure estimates in section 3. And then finally, in charge question 4, we've asked for input on quantitative and qualitative approaches for considering aggregate exposures. And we primarily apply quantitative methods of aggregate in our estimation of total exposures in air or water in section 3, which is then carried forward into the risk characterization in section 5. So I'll wrap up with just a few more slides to remind you of some of the key points that Jeff and Rochelle raised earlier today. And a reminder that the methods we've asked you to review are intended for application in the context of risk evaluations that serve as decision support documents for risk management. So today we've presented a range of methods used to perform discrete analyses, but in the context of the supplement, our aim was to integrate those analyses to tell a cohesive story. So for example, our analysis of the surface water pathway for 1,4-dioxane integrates several of those methods to understand the exposures and risks that result from multiple sources. So to do that surface water analysis, we evaluated releases, as Franklin described, based both on reported releases as well as releases modeled using Monte Carlo methods. And then, as Brian described, we used several parallel analyses to apply reported and modeled releases. We used parallel analyses to take the reported and modeled releases to estimate water concentrations from a range of sources, both alone and in combination. And then we calculated risks from drinking water with monitored or modeled concentrations under a range of scenarios to define the conditions under which we predict risks above a given benchmark. And that integrated story can now be used to inform unreasonable risk findings. Now, EPA believes that the 2020 risk evaluation for 1,4-dioxane already indicates unreasonable risk. This supplement is intended to complete the story for 1,4-dioxane by identifying whether additional conditions of use contribute to that unreasonable risk finding. So we ask that you offer your comments and feedback on our methods with an appreciation for the context in which these methods are being applied and how they may be integrated to tell a more comprehensive story around risks from a given chemical. And in particular, we'd like you to consider how the methods that you're evaluating in response to the charge questions support the supplement's objectives and application as a decision support document, and to consider how the refinements that you suggest can increase the supplement's value as a decision support document. So that concludes the EPA presentations, and I think we're all looking forward to hearing your feedback.
Okay, thank you. And are there any clarifying questions from the committee? It looks like there are none. I don't want to just rush forward. I know we had many clarifying questions as we went along. But if there are no clarifying questions, I'd like to thank the EPA presenters, each and every one of you, for really good presentations, very informative, very relatable. Oh, I do see a question now from Dr. Ginsburg and some others coming in.
Yeah, sorry, I wasn't sure if you were asking
So
for questions.
please identify yourself.
Oh yeah, this is Gary Ginsburg. Wasn't sure if you were asking whether we had questions just for this speaker or for the overall session. So if it's going back to other things that we've heard today, is that what's on the table now?
So yeah, this is George Cobb speaking. It is surely for any of the presentations that we've heard this day.
All right, so then my follow-up is regarding land releases from down the drain, but even from commercial, commercial or consumer down the drain releases, and land releases that's not related to a landfill per se, but related to septic systems. Has septic systems been thought about? And therefore contaminating groundwater and putting wells, private wells at risk.
Hi there. We did not consider that in this particular supplement, but we invite comment on how we might consider that in future risk evaluations.
A follow-up, I guess, is in the modeling for I'll call it the validation case study exercises, where a certain population size is assumed to have their down the drain releases draining into a river watershed. It's assumed that they're all coming through a POTW, although those are not specified which ones and where they're located. So is that right? That whole, let's say there's 50,000 people, all 50,000 are modeled to come through some unnamed POTW rather than having septic systems that may be contributing to the watershed? Is that the way EPA modeled it?
Hi, this is Brian Groza, and that's correct. And we did find there was a slight overestimation in some of those analyses in the case studies that may include that as a factor.
Right. I mean, so the overestimation could in part be because, not all those people are necessarily contributing to a POTW, right?
Correct, yeah.
Okay, thanks.
Thank you. Dr. McKenzie?
Lisa McKenzie. So I had a couple questions on the scenario around the land scenario for hydraulic fracturing. And I just was wondering how you came about considering the surface impoundments and not other potential ways that hydraulic fracturing fluids could be contaminating groundwater. Did you consider other pathways that you then eliminated, or how did you settle on that one scenario via surface impoundment?
Hi, this is Sean Shiflett. We relied on the data that we had to consider release to surface impoundments and the models that were available to us to complete that assessment. Again, we welcome any comment or any advice on how we might think about that differently in future risk evaluations, but this assessment was limited to the data we had and what we could do.
Thank you. Dr. Ottinger?
Yes, thank you. This is Marianne Ottinger, and as a new addition to the SAC, I've been very impressed with not only the amount of data, but how it's been organized and the vast amount of information that has been had to be dealt with in one way or another. So I have several questions that are more general. And first would be that I'm very gratified to hear the consideration about lifespan and years of exposure and separating out early exposures versus later. And so I'd be very interested, this is just a comment, I'd be very interested in where this goes in the future, and would be very interested in effects in the more senior aging population. In terms of questions, I wondered if there is any way to include, or has it already been done, exposures to multiple chemicals. It was kind of alluded to in one discussion, and I was wondering if there was any indication of any modification of effects.
This is Susanna Wegner. So we are not directly addressing cumulative exposures, certainly not in a quantitative way in this assessment. You know, we acknowledge in a very qualitative way in our pest discussion that factors like co-exposures to chemical and non-chemical stressors can influence your susceptibility. If to the extent that we're exploring that in a more quantitative way, the cumulative framework document that the SAC reviewed several months ago is sort of represents our thinking around cumulative currently, and is an approach that's for how we'll consider that for the phthalates as a group.
Right. Yeah, no, it's very difficult, and I appreciate your response. You know, it goes to the question of, is there a situation where multiple exposures aren't additive? In other words, you know, could there be dose-dependent effects or low-dose effects or inverted U-curve kind of responses? So I wondered if there was a way to deal with some of these potentially nonlinear effects in the models.
Sorry, was there a question?
Yeah, if there's a way to deal with nonlinear effects in the models, is that part of how the Monte Carlo then would function? You know, would that help with nonlinear effects?
So, sorry, I'm sorry. Can you repeat the question in the context of the exposure or the hazard side of it?
In the context of effects of exposure in the models.
I'm afraid I'm not fully understanding the question, but is there another? Can you try rephrasing it?
Well, let me. It's actually not meant to be that complex. It's just as some chemicals, in my experience, don't have a linear effect with dose, and I guess my understanding is one of the reasons to use more qualitative methods, because of some of those types of uncertainties, would be to deal with perhaps some nonlinear effects. And that's basically what I'm asking.
Yeah, so this is Susanna Wegner. Yes, that's a great question and a challenge for us to explore, and we welcome any advice you have on how to pursue that.
Okay. All right. Sorry. Last question. I'm assuming the single year models that you all are using now, the intent would be in subsequent years, perhaps to broaden it to include multiple years.
Are you talking in the context of the air pathway?
Yeah. I think that's where it was mentioned.
Yeah. So that's what Kevin was describing. So originally, that analysis was limited to a single year of release data. And what we've done in the current assessment is to also look at other years of release data and to at least do a sort of higher tier analysis of the full data set.
Mm-hmm.
So, to the extent that that adds to the analysis, that's certainly on the table.
That's great. Thank you very much.
Absolutely. Thank you.
All right. Dr. Chase.
I have a very, very specific question that is actually a point where I kind of fell off the wagon and could not follow the logic. And because I'm at this particular point is very important to my thoughts about the upper end calculation sentinel exposures, it's important that I not misunderstand what you're saying. So I'm going to present the question, and I'll be flabbergasted if you can just off the top of your head answer this, but maybe you could take a look at this until tomorrow or something, if not. If you look at lines 3623 to 3625, where you're discussing, well, let me read this to you. EPA, this is a quote, EPA does not have reasonably available information on actual concentrations of 1,4-dioxane in leachate for most landfills, and therefore selected landfill leachate concentrations are based on potential for risk to human health. I just don't know what that means. And so for starters, I'd like you to explain the sentence. I apologize if I'm just not being too bright here about this, but I just couldn't understand it. However, when I explored this further, maybe I'm going down the wormhole here, but is this the groundwater concentration at 1 in a million cancer risk as back calculated in your Excel sheet 21? And then going even deeper, the threshold concentration tab with Excel sheet 20. How does this work? And what I'm exploring here is somehow in your calculation, did you end up with sort of a capped distribution on this? I don't understand the logic flow in that, so maybe you guys could tutor me on that, if not now, later.
And this is George Cobb. You folks from EPA feel free to address that, but if you can't address it fully and directly right now, we can certainly revisit it during the charge questions, but this would be a preview of the kind of information that would be needed.
Yeah, and also, George, I have that written out, so if they need to have the written form of that, I'll send it to give me instructions. How do I do that to relay to them?
You can just email that or send it in the chat, either one.
Okay, thank you.
Hi, this is Sean Shiflett. I'm not sure I quite captured what the question was. So if the question is about the leachate concentrations, we based it on a hypothetical based on the release data, and kind of bounded the assessment on what we could find. But maybe you can repeat the question and maybe I can answer it better, or
I put it in, yeah, I put it in the chat. And as I'm pointing out, besides the fact that I just need you to explain to me the logic of that sentence, as well as how that relates to
these points in the Excel, because I'm obviously making a mistake somewhere. And my concern is based on that and what you just said, are you somehow artificially bounding the distribution so that if you're talking about sentinel and you're interested in the upper tail, is this logic mean that you bounded the upper tail? So I was trying to play with that, and that's where I got very confused, and maybe it's just I'm misunderstanding your logic. So maybe you could help me with that.
Do you mind if you can read the question that you put in the chat?
Yes.
Because the public that are watching on YouTube or
sure,
to be a part of the record, they won't know what's in the chat.
Okay, I'll reread it. In the document lines 3623 to 3625, EPA states, quote, EPA does not have reasonably available information on actual concentrations of 1,4-dioxane in leachate for most landfills, and therefore selected landfill leachate concentrations are based on potential for risk to human health. So for starters, what does that mean? And then in looking at the actual concentrations calculated, and this would be Excel sheet 20 and 21, quote, this is my question, is there groundwater concentration at 1 in a million cancer risk as back calculated in Excel sheet 21? And under the threshold calculations tab in Excel sheet 20, what is the logic for these distributions? And this is important to me because EPA claims they calculated a sentinel exposure, but I don't understand the logic flow here.
Hi, this is John Shiflett. So we did not have a wide wealth of information about the concentration of 1,4-dioxane in leachate. So when we conducted our assessment, we ran our numbers based on where we started to see risk to human health. So the upper bound.
I don't know what that means. I don't know what that sentence means. I'm not debating you. I don't understand what you mean by that sentence. I mean, did you you had to start putting numbers in somewhere. Where did these numbers come from? When you say we started the assessment at the level of whatever, what numbers are you using? This is where I went down the wormhole in Excel sheet 20 and 21. I mean, in order to create this distribution, I'm trying to look for what numbers did you pick to put in the assessment?
Yeah, this is Susanna Wegner. So as Sean is saying, the numbers are based on where we began to hit a risk benchmark that was sort of in the realm of the thresholds that tend to be in the conversation around risk management, right? So once we hit a benchmark of 1 in a million cancer risk, that was where we wanted to go high enough to be able to know what is the leachate concentration that would result in a 1 in a million cancer risk or greater. And so we took the analysis at least as far enough as required to hit that benchmark to give us a sense of like, okay, we don't know what the actual on the ground concentrations are in any given location, but we can at least map out under a hypothetical, if your concentration hit X value, there's where you would start to see a cancer risk. Does that make sense?
That makes sense. However, so that makes sense to me. But my quest, which was to look at a distribution that could be considered sentinel, just isn't there, correct? Because you're just doing a calculation to in good faith pretend to present, what would the concentrations have to be to hit these kinds of levels, which is a very different question than saying this is a distribution, the upper 95th percentile of which could be considered sentinel.
And I think this is a question that we, again, would absolutely welcome SAC input on in how we define what sentinel looks like. For our purposes, you know.
Yeah, well, like I said, I'm not debating your approach. I just wanted to be sure I wasn't misunderstanding
So
what your calculations were. So thank you for that.
Yeah, I hope this answered your question. I think we need to move along. If we need to circle back to this question in the charge question answers, that's fine. Right. But I think we need to move on to Mr. Wright now. Mike, are you there?
Yeah, I am. I just had to take it off on mute. This will be very short and simple. Okay. I found the PowerPoints to be very useful as an organizing tool. Mm-hmm. And I know they'll be in the public record eventually, but will the committee have access to them over the next few days? Because it would be good to be able to go back and review them as an aid to memory. Was that?
Your voice disappeared, Mr. Wright.
Let me try again.
We missed like a few seconds.
Yeah, I found the PowerPoints very useful. I know they will be in the public record eventually, but could they be put in? Could the committee have access to them relatively soon so that we can use them as a kind of an aid memoir?
The PowerPoints are already available in the docket for anyone for the
They're
public.
already there. Okay.
Yes.
That's all I wanted to know. Thank you.
You're welcome.
And Dr. Miglino?
Hi, Andrew Miglino. I just had a couple questions about the loadings for the surface water modeling. Just some clarifying questions here. Really all about the commercial side of things. So the first question is, I understand that you use the mean and the 90th or 99th percentile for non-commercial and commercial loadings respectively. I just want to make sure, because the Excel files appear to use the 99th percentile, but the text says the 90th percentile, which was actually used for the modeling there.
Hi, this is Brian Groza. Thanks for pointing out there's a discrepancy there. I can find the answer and clarify that for you.
Okay, thank you. And similarly, in tables G2 and G4 in Appendix G, those appear to be trying to show the same information, the commercial and non-commercial loadings respectively, but the loadings presented in G2 for the commercial entities do not appear to correspond to anything in G4. And so I was just confused, either are they different on purpose? And if so, what is being presented differently between the two? Or if they're supposed to be the same, I assume that G4 is the correct one.
Okay, I'll have to pull up those figures and I can clarify that for you as well.
Yeah, that'd be great. Thank you. And one last question. Paint was recognized, I believe, in the last SAC as an important commercial product here. In reading the justifications for the paint loadings in, I believe it's Appendix F, the discussion seems to be really focused around automotive paints. But there is some discussion of rollers and other application techniques, which at least implied in my read that it was more than just automotive use of paint. And even the title with floor lacquers seemed to suggest that. is the discussion really just about automotive paint, or does it capture other paint and lacquer uses? And if it's the latter, is there discussion of that somewhere in this document as well for why it's included or not included?
This is Franklin Hall. Let me pull up that part of the appendices and then get back to you on that. We can talk about that, or I can bring that back up during the Q&A for the engineering portion of the charge questions.
That'd be great. It's appendix F47 is where that's discussed, I believe.
Okay, thank you.
That's all I had. Thank you.
And Dr. Portier.
I hate to say it, George, I wanted to go back to Dr. Chasson's discussion and just clarify one thing. So if they back calculated groundwater concentration for 1 in a million cancer risk, if it were a deterministic model, it's just an equation, we work backwards. So part of the confusion is the word distribution. So does that mean that they're doing this back calculation among a set of landfill scenarios to back calculate for 1 in a million cancer risk what groundwater concentrations would have been like under that scenario? And that's because I understood the concern, and to me the key word was, how did I get from one back calculation to a distribution? Is that right, Dr. Chasson? Is that part of the confusion?
That's correct, Dr. Portier. There were multiple levels of confusion. And by the way, I think that the value that they calculated is useful to have been calculated, but for reasons that have nothing to do with me looking for a sentinel number within a distribution, because I can't figure out, just like you said, I just can't figure out how the distribution was set up. And now it appears that, well, that's because I don't think there was one, but we can discuss this later. But I truly appreciated the explanation, so I can go back and play with this a little bit better. So thank you for that.
So Ken, did you have a question for the agency, for EPA specifically?
No, it was kind of a question for Dr. Chasson about the where is the uncertainty in her concern here? You know, and I think it's the difference between back calculating one number and then coming up with a distribution. And then Dr. Chasson's concern is that final distribution, because of this methodology, might be truncated on the higher or the lower end, right?
Exactly.
And then it's kind of like a self-fulfilling prophecy at that point, right? I have a distribution that's truncated that doesn't give me high cancer risk because of the way I calculated it back again. I mean, I understand where EPA is trying to go there.
Yeah.
And it may be just the way they described it. It's just not adequate enough.
Yeah.
Understood.
Yeah. Okay. There's a question from Dr. Rubin.
Hi, Rainbow Rubin. I hate to say it too, but I'm going to go back to the DDT loading values if it's okay.
That's fine, because I had some similar questions, perhaps.
Okay. I just wonder if there's any validation that the 90th percentile of household DTD approximates commercial use. I'm just wondering if this could underestimate loading, because in some cases we would expect 0 level of non-commercial DDT loading, like textile dye and spray polyurethane, but high levels for commercial DDT loading. Thanks.
We have the EPA presenters.
Hi, this is Brian Groza, and this is an area where we welcome feedback on what an appropriate level would be here, where we just assumed that the high end conveyed to the commercial usage as well.
Gotcha. Thanks.
Thank you. So at the risk of extending this, I have two questions. One is about slide 77, where the releases in the North Carolina River, I believe it was, were depicted, and it seemed like your models were doing a good job predicting central tendency or mean concentrations. And I'm curious as to whether your models were tested or whether they actually give good representation of upper bounds or high centile concentrations, because the bounds on some of those concentrations were pretty high in that graph. And this is George Cobb asking the question.
Hi, this is Brian Groza again. I would say that with the proper input data, it could be targeted to those higher level concentrations. The means are more of interest to us for the longer term exposure scenarios that we're looking at. And also because the data available to us are these annual releases and these mean flow values that are modeled in the NHD plus data set. The methodology does tend to target that average concentration.
So yeah, this is probably something that we'll want to revisit in the water sets, because if you don't have a lot of data, this probably maybe means not where you want to be. All right, slide 84. There are a lot of data points, excuse me, slide 83. There are lots of data points represented, but how many facilities are actually represented in that particular figure?
Hi, this is Brian Groza. Is that the drinking water facility data?
Yes.
I can get back to you on that. I don't have the number off the top of my head.
And thank you. Again, we don't necessarily expect you're going to have all these answers at the tip of your tongue, but kind of give you a preview of what's out there. Okay. Oh, I see Allah has his hand up.
Right. Just my hand up, not a question, but I noticed Dr. Ginsberg, he posted on the chat a link to a website of the North Carolina environmental quality, the website there, and the public who are listening on YouTube and to be part of the record, if I can or Dr. Ginsberg can read the website, the link exactly where they can go and obtain this link. Would you like to read it, Dr. Ginsberg, or I can read it?
You're on mute, Dr. Ginsberg.
Okay, now I think I'm off mute. Let me find my note. Yeah, so this is the, with respect to POTW outfalls in a particular study area, where there's actually reasonable data also for drinking water intakes. So the website is the North Carolina DEQ 14, I'm sorry, no, that was my note. I guess I should read my note too. So North Carolina DEQ 14D Cape Fear Basin Study includes source evaluation and POTW data. And the link is Cape Fear River Basin 1,4-dioxane study, then a vertical bar, a vertical line, NCDEQ.
Right. Thank you very much, Dr. Ginsberg. This is Alak Kamel again. And if anyone missed the website, they can send me an email and I can forward this website to them. Thank you very much.
Well, and then the other one I put in the chat was a newspaper article that provided information on outfalls and drinking water effects in the Pittsboro, North Carolina area. And it's 1,4 POT, and it's the headline from the newspaper was Burlington releases slug of 1,4-dioxane into Haw River, enters Pittsboro drinking water, and it's NC Newsline.
Thank you. And please consider when you put things in the chat that not everybody will have access to it. Only those in the Zoom link are going to access it, but those who are watching on YouTube and the public will not, and we will have to post it in the docket. So that's why if there is anything that is needed to be added, a reference or any website, please email it to me and Dr. Cobb, and we will make sure that it reaches everyone through the docket. Thank you.
All right. Well, thanks everyone for getting through this much of the day. We do have public comments. We're a few minutes late. I think EPA has asked for a few minutes maybe to get the public comments pulled together. So maybe we can take a 5-minute break, or do you folks from EPA need 10 minutes to get this set up? What do you think? Charlene, Allah?
Sorry, I was muted. 10 minutes, I think, is okay.
Okay. So let us reconvene at 27 after this hour.
Thank you.
Right. Welcome back. I hope the agency has the list of speakers, public commenters together. Allah, do I have a list of those public speakers?
Yes, I sent them to you by email. If you can check your email, you're going to find it there.
So was that a few days ago or today?
Well, was yesterday a list of 9, and then they were updated today by a list of 6.
I have it here. Thank you very much.
You're welcome
for helping me stay organized. All right. So again, welcome back, everyone. This is George Cobb, and I'm going to introduce our speakers. Our times are 5 minutes, and please hold your comments to within that time frame. Allah or I will try to help you keep track of that time if you start to run over time. So with that, I'd like to introduce Paul DeLeo from the American Chemistry Council.
Okay. Good afternoon. I'm Paul DeLeo, and I'm the Senior Director of Chemical Management at the American Chemistry Council. ACC is an industry trade association representing more than 190 businesses creating manufactured products that make our lives healthier, safer, more sustainable, and more productive. I wanted to begin by thanking all of you who have volunteered to participate in this Scientific Advisory Committee on Chemicals. You have a challenging task ahead of you, and I'm grateful for your time and commitment to this important program. As we approach the 7th anniversary of the prioritization of 1,4-dioxane, I think we can all agree that the process for risk evaluation by EPA is not sustainable in its current form. According to EPA's regulatory agenda, a proposed risk management rule for 1,4-dioxane is not expected until August 2025, 2 years from now. Though EPA has not solicited feedback from the SAC regarding the broader risk evaluation process, we believe the SAC is in a position to provide recommendations to EPA to make that process more efficient, effective, transparent, and sustainable. I wanted to share 4 opportunities that I hope you might address so that EPA can get back on track to meet its 3-year statutory requirement for finalizing risk evaluations of high priority chemicals under TSCA. First, scoping. In the draft supplement to the risk evaluation for 1,4-dioxane, EPA assessed the risk of consuming groundwater contaminated by landfill leachate and hydraulic fracturing waste. I hope everyone would recognize that groundwater contaminated by improper disposal of waste such as these is inherently unsafe as a source of drinking water. In addition, this is not an intended manner of disposal of a chemical substance. Groundwater contamination reflects failure in disposal practices that should be corrected, but would be better addressed through other EPA authority or state authority rather than through TSCA. Consequently, EPA could have quickly scoped out this potential route of exposure in its risk evaluation. Second, problem formulation. The draft supplement lacks a problem formulation against which results can be compared to determine whether EPA's stated questions have been answered. For example, in examining data on the presence of 1,4-dioxane in finished drinking water across the US, EPA reported that it was detected in 11% of samples. Then it goes on to report that lifetime cancer risk at the 95th percentile concentration for those 11% of samples was below the 10 to the minus 6 benchmark. So greater than 95% of the 11% is below the benchmark. However, EPA went on to conduct an additional modeling analysis that indicated that public water systems serving a combined population over 2 million people exceeded the cancer benchmark. And while this is a large number, it's still less than 1% of the US population. The more important question here is, what is EPA's population protection goal? Is it 95th percentile, 99th, 99.9? I don't have a recommendation, but to say that in the absence of problem statements and performance criteria against which results are compared, additional extraneous analyses will be conducted, consuming precious resources. Third, tiered analysis and decision frameworks. Many of the analyses conducted within the 1,4-dioxane risk evaluation lack a decision framework to inform whether the results are sufficient or whether additional refined analyses may be necessary. For example, there are 3 analyses within the fence line screening approach for facilities emitting 1,4-dioxane to air, including an approach using multiple years of emission that is based on a recommendation of this SAC. These approaches are characterized variously as pre-screening, screening, full screening. However, there is actually no screening that occurs among them and no real relationship from one analysis to the next. EPA needs to establish decision criteria associated with each analysis and then consider whether further refinement is necessary in the context of a problem formulation. And lastly, with respect to data sources, there are numerous obsolete data sources that populate the various exposure estimates in the draft supplement. The most notable is that regarding residual concentrations of 1,4-dioxane and ethoxylated materials, especially surfactants. Pressure to reduce concentrations of 1,4-dioxane in consumer products over the past decade has been substantial. New York State has limited the maximum allowable concentration of 1,4-dioxane in many consumer products to 1 part per million by the end of this year, and a database of 1,500 products that have received a 1-year waiver from compliance report a median concentration of 5 parts per million. EPA needs to improve its data sources to reflect current conditions and update its analyses and risk conclusions. It's imperative that the SAC provide meaningful recommendations to EPA to improve its risk evaluation process overall and revise this draft supplement so that results are based on best available scientific data and information which can support the risk determinations for 1,4-dioxane under its conditions of use and have utility for potential risk management. Please, whatever you do, don't give EPA more work to do. Give them the tools and guidance so they can make risk-based decisions more effectively. Thank you.
So thank you. And we will ask questions at the end of the sessions, all the presenters. So if you'll hang around, there may be questions, sure. Please. All right. Next presenter is Kate Jacobus from the Cleaning Products Association. We have that speaker. Kate Jacobus.
She hasn't confirmed. She did register, but did not confirm that she's coming. So maybe you can try her again in the end.
Okay. Next on the list is Jonathan Calmus Katz from Earth Justice.
Thank you. Let me just get this on my screen. Can you hear me all right?
Yes, we can. Maybe if you speak up a little bit.
Sure. Good afternoon. I'm John Kelmus-Katz from Earth Justice. Last Friday, we submitted written comments on EPA's supplemental risk evaluation for 1,4-dioxane, and I encourage the members of the SAC to review those if you've not yet done so. Today, I wanted to focus on 3 ways the supplemental evaluation understates 1,4-dioxane's real-world exposures and risks. First, relevant to charge question 1D, EPA understates the length of time that people are exposed to 1,4-dioxane in their air or drinking water. EPA stops counting exposures after 33 years because it assumes that people will not live in the same place for longer than that, despite all evidence to the contrary. This assumption improperly equates a change in address with an end to 1,4-dioxane exposures, even though most moves within the United States occur within the same county, and 1,4-dioxane is known to contaminate regional drinking water sources across large swaths of at least 45 states. EPA ignores multiple studies cited in our comments that document vast racial, cultural, and socioeconomic disparities in geographic mobility. Due to discriminatory land use policies and real estate practices, Black households are far more likely to spend multiple generations in low-income fence-line communities than white households. And Indigenous populations have long-standing cultural and sovereign ties to their land that EPA completely disregards. Finally, even if most people could somehow escape their 1,4-dioxane exposures, the Toxic Substances Control Act would still require EPA to evaluate the risks to potentially exposed and susceptible subpopulations who cannot or do not leave. EPA can't protect those with the greatest exposures to 1,4-dioxane if it abandons them after 33 years, ignoring more than half a lifetime's worth of exposure and leaving them with little more than real estate listings to try and fend for themselves. This is just an unacceptable passing of the buck, grounded in exposure assumptions that are contrary to the best available science and irreconcilable with EPA's TSCA obligations. Second, relevant to charge questions 1C and 4C, EPA underestimates the frequency and duration of occupational exposures to cleaning products, dish soap, and other goods containing 1,4-dioxane as a byproduct. Specifically, EPA assumes a single dermal exposure event per day for all those workers, lasting as few as 20 to 30 minutes. It is self-evident that domestic workers, custodians, and restaurant dishwashers use dish soap and cleaning products throughout their work shifts for far longer than half an hour. EPA understates their occupational exposures and then compounds that error by failing to consider their combined exposures from 1,4-dioxane on and off the job and from multiple exposure routes. Now, in its presentation this morning, EPA attributed this shortcoming to limitations in the dermal models it was using. I encourage you to scrutinize that. Exposure duration is not an immutable characteristic of the dermal model. It is a variable input that EPA could have changed had it wanted to. Third, relevant to charge question 3, when calculating drinking water risks, EPA fails to consider acute risks from contaminated groundwater supplies. Now, EPA admits that ingestion of 1,4-dioxane causes both acute and chronic harm, but here too, the agency blames its modeling, claiming that it lacks the capacity to model acute groundwater risks. As explained in our written comments, that is not the case. There are available groundwater models and modeling resources that EPA could have used in this evaluation. EPA chose not to use them. These errors have real-world impacts because EPA's unreasonable risk determinations trigger its obligations to regulate 1,4-dioxane under TSCA. By underestimating exposures and risks, EPA lays the foundation for a risk management rule that would leave impacted workers and communities exposed to unsafe levels of 1,4-dioxane. There are custodians, domestic workers, and dishwashers in Houston and Brunswick County, North Carolina, and other communities who are exposed to 1,4-dioxane throughout the day, at work and at home, and who will remain so for their entire lives. I urge the SAC to keep those potentially exposed or susceptible subpopulations in mind this week, and to advise EPA on how it can better account for their real-world exposures and risks. And with that, I thank you for your time.
Okay, thank you. And our next presenter will be James Kim from the American Cleaning Institute.
Good afternoon. My name is James Kim. I am the Vice President for Scientific and Regulatory Affairs at the American Cleaning Institute, or ACI. ACI members include the formulators of soaps, detergents, and cleaning products used in household, commercial, and institutional settings, and the companies that supply ingredients and finished packaging for these products. On behalf of ACI, I am pleased to be able to share with the SAC some important concerns our members have about the methods used and the conclusions being reached in the draft supplement to the risk evaluation for 1,4-dioxane. ACI notes that it is inconsistent with the scientific standards that Congress added in 2016 to Section 26 of TSCA and EPA's own procedural regulations to make use of new models and approaches prior to their peer review in a formal risk evaluation, as EPA has done here. For reasons discussed in written comments that ACI has submitted to the docket, we also think that there is additional work that should be done by the agency to improve the human health hazard characterization for 1,4-dioxane and to correct certain features of the carcinogenicity assessment, topics which EPA has unfortunately left off the table for SAC's review. ACI is concerned that the scientific deficiencies noted at the time of the 2020 risk evaluation were not addressed and that they continue to inform the 2023 draft supplement. These are addressed in detail in an in-depth technical analysis that ACI has included in our written comments to the docket. ACI notes that other respected authoritative regulatory agencies have recently concluded that 1,4-dioxane is a nonlinear threshold carcinogen, such as the European Chemicals Agency in 2022 and Health Canada in 2021. ACI has certain procedural concerns about the current process that are beyond the SAC's control, but of which we think you should be aware. EPA has only recently made publicly available certain background documents concerning the draft supplement. It is unreasonable for EPA to expect ACI and other interested parties to review these recently released technical materials and to provide public comment by September 8th, the deadline that EPA has refused to extend. It is also insufficient time for members of the SAC to carefully review submitted materials and comments and to credibly respond to charge questions concerning, as described by EPA, quote, recently developed tools and approaches that have not been peer-reviewed for use in TSCA risk evaluations, end quote. We encourage the SAC to carefully consider and provide comments on EPA's use of the fence line communities version 1.0 as it has been applied in the draft supplement. SAC's comments on the initial version of this screening approach stated that SAC, quote, had difficulty reproducing results that were relevant to understanding and reviewing the document and indicated multiple limitations and uncertainties, end quote. And SAC made recommendations for improvement at that time. And we encourage SAC to determine whether and how effectively EPA has improved the method. ACI suggests to the SAC that it should advise EPA to prioritize the use of existing data from published risk evaluations and other sources rather than relying on new and novel modeling results. ACI recommends that SAC suggests that EPA revise both the occupational and down the drain assessments for dish soap and dishwashing detergent. The agency's assessment of exposure during the occupational use scenario for dish soap and dishwashing detergents is deficient because EPA has used data from a formulating and packaging plant rather than estimates for a worker washing wares. If this scenario is to be used for evaluating occupational exposure to 1,4-dioxane in a formulation facility, EPA needs to update some of its assumptions. The EPA derived a limit of detection of 2.1 milligram per cubic meter, has significant uncertainty, and given that all the air samples were non-detects, this is a significant factor in the risk assessment. In the current scenarios, EPA used the estimated LOD and 1/2 the LOD for the worker high-end and central tendency exposure estimates. These values are 2 to 4 orders of magnitude greater than the risk evaluation inhalation estimate for consumer exposure. ACI recommends that when evaluating and modeling risk for workers washing dishes and down the drain environmental risk, the agency should estimate concentrations of 1,4-dioxane that may be present under current industry standards, such as the New York State DEC's maximum allowable concentration of 1 ppm by the end of this year. A reasonable worst-case scenario could be generated based on data from the New York DEC 1,4-dioxane approved waiver spreadsheet which would suggest the agency can conservatively assume a concentration range of 1,4-dioxane in dishwashing products as 2 to 15 parts per million with a median of 8.4 ppm. This would be a highly conservative estimate as the figures do not include products that already meet New York DEC's established maximum allowable concentration.
If you can wrap up, please.
In closing, ACI encourages the SAC to A, recommend EPA reevaluate its conclusions with regard to the carcinogenicity assessment and the use of the linear approach. B, recommend against EPA's use of its new modeling techniques for formal risk evaluations until the SAC has completed its peer review. C, recommend EPA make better use of publicly available information regarding 1,4-dioxane content in cleaning products and to incorporate them into an enhanced draft supplement while also collaborating with ACI on gathering workplace monitoring data. And finally, we also encourage the SAC to review ACI's in-depth technical comments in Appendix A of the written comments that we have submitted to the docket. And thank you very much for this opportunity to speak before the SAC.
Thank you.
All right, thank you. Next commentor is, let's see, it's Rupa Krithvasian.
Shritivasan, thanks.
Sorry.
Not a problem, it's a hard one. Can you hear me okay?
Yes.
Yes.
Good afternoon. I'm Dr. Rupa Krithvasian. I'm Director of Research at Defend Our Health, a nonprofit public health organization that works to protect vulnerable populations from exposure to toxic chemicals. We've also submitted written comments on EPA's draft risk evaluation for 1,4-dioxane. We'd like to commend the EPA for their improved assessment of 1,4-dioxane risks. The assessment appropriately makes an unreasonable risk determination for the whole substance. It includes additional conditions of use absent in the 2020 assessment. It includes 1,4-dioxane as an industrial byproduct of the PET industry. And it's correct in its assessment that there is unreasonable risk posed to fence line communities due to 1,4-dioxane releases from industrial sources to drinking water. However, the current draft assessment falls short significantly in appropriately determining risk, especially from the PET industry, which is the biggest emitter of 1,4-dioxane to water and air in the US. We'd like to highlight two specific ways in which the assessment falls short, and by doing so allows the continued exposure of vulnerable populations and compounds environmental injustice. First, related to charge question 4, the assessment ignores aggregate exposures and risks across different routes, pathways, and conditions of use. So currently the draft assessment does not aggregate cancer risk from inhalation, oral and dermal pathways. It doesn't quantify the full extent of risks from exposure to 1,4-dioxane from multiple sources. And it doesn't consider the risks to fence line communities and workers who live at the fence line from one or multiple facilities and who are exposed via multiple conditions of use. The arguments provided for ignoring aggregate risks are weak. In particular, EPA argues that in the case of risk to fence line communities, quantifying aggregate risk was unnecessary as locations with above benchmark aggregate cancer risks from multiple facilities were already identified as having cancer risks that exceeded the benchmark due to exposures from individual facilities. However, this misses the point of assessing aggregate exposure. The goal is to determine the full extent of risk, not simply to categorize a location as above or below threshold, which provides no real indication of the severity of risk. Because the 1,4-dioxane assessment will serve as a standard for future risk evaluations, it is imperative that the current assessment be based on the best available scientific methodology that appropriately accounts for the full extent of aggregate risk. Second, the risk evaluation did not include any demographic analysis on disproportionate risk burdens on people of color, low-income people, or other vulnerable communities on the basis of socioeconomic or cultural status. Census data indicates that fence line populations near PET facilities in particular are disproportionately lower income or people of color. Almost half are low income and almost half are people of color. The assessment fails to analyze in any detail or integrate the scientific evidence that shows that people of color are, in addition to being more highly exposed, also less able and likely to relocate from areas of high risks to areas of low risk, are uniquely susceptible to the health effects of toxic air pollutants and co-exposed to other chemicals, and experience cumulative impacts from a combination of other psychosocial stressors, including racism, poverty, lack of access to healthcare, among others. By underestimating total exposure and risk, especially for low-income communities of color, EPA ignores the requirements of the revised TSCA to utilize the best available science for evaluating risks. In order to fully assess the risks associated with 1,4-dioxane exposure, EPA must more completely and precisely assess the risk to fenceline communities, including more in-depth demographic analyses that take into account economic and racial disparities that contribute to exposure and risk. We suggest at minimum demographic analyses similar to those developed for the recent National Emission Standards for Hazardous Air Pollutants, also called NESHAP, such as for the recent Hazardous Organic NESHAP for the synthetic organic chemical manufacturing industry. We urge this committee to consider the real harms of fully accounting for risks faced by fenceline communities as they assess the merits and inadequacies of the draft assessment this week. Thank you so much for your time.
Thank you. Our next presenter is Swati Ryasam from the University of California. I believe that's San Francisco.
Yes. Hi, that's me. Thank you. Hold on one second. Let me put my comment. So good afternoon. My name is Swati Ryasam, and I'm a science associate at the University of California, San Francisco's Program on Reproductive Health and the Environment, or PRE. I have no conflicts to disclose. As reflected in our detailed written comments, while there are notable improvements to the draft supplement for 1,4-dioxane, there remain significant deficiencies that do not represent the best available science, which EPA is required to use under TSCA. I have two comments to this effect. First is that the draft supplement continues to rely on deficient methods for non-cancer dose response analysis and risk characterization employed in the original TSCA risk evaluation. EPA uses a margin of error or MOE approach that is overly simplistic to characterize risk. The MOE, which relies on a point of departure with no extrapolation to lower doses, does not estimate the proportion of the exposed population projected to experience a specified health endpoint or the number of individuals affected, and it perpetuates the scientifically flawed notion that there exists a safe or no risk level of chemical exposure in a diverse population. Authoritative bodies such as the NAS and the World Health Organization have outlined superior methods for risk estimation. At PRE, we applied the WHO methodology to estimate risks for adverse effects from chronic inhalation and oral exposure of 1,4-dioxane at doses relevant to the general population exposures assessed in the draft supplement. Our analysis found that the risks of adverse effects to the olfactory epithelium as at reported inhalation exposure levels and the risks of non-cancer liver effects at reported oral exposure levels are very high. Multiple conditions of use have estimated exposures well in excess of the levels associated with a 1 in 1,000 incidence of effect. For example, EPA's estimated maximum daily dose of 1,4-dioxane in drinking water from the ethoxylation byproducts condition of use is 10 times the dose associated with a 1 in 1,000 risk of non-cancer liver effects. In the recent TSCA risk management rules, we've been able to see the downstream impacts of EPA's use of this flawed MOE approach. For example, EPA used the MOE approach to develop workplace standards, or ECHLs, for the methylene chloride and perchloroethylene proposed risk management rules. But using the WHO approach, these proposed ECHLs would result in very high risks of non-cancer effects to workers. For methylene chloride, that ECHL would be a risk of adverse liver effects as high as 1 in 350 workers. And for perchloroethylene, the exposure at the proposed ECHL could have risks of adverse neurological effects or decrements in visual memory as high as 1 in 200 workers. We have and we continue to recommend that EPA use probabilistic dose response methods like the WHO method to better inform its unreasonable risk determinations and to provide the necessary benefits analysis for use in the risk management process. EPA's continued failure to abandon the MOE approach and employ the best available science to quantify non-cancer risk means that these risk evaluations and their resultant risk management rules will continue to systematically underestimate risk and fail to meet EPA's goal to protect human and environmental health and undermine EPA's work toward environmental justice. To my second point is EPA's flawed assumptions in the draft supplement around residential occupancy to estimate lifetime exposure risk, which builds on Mr. Kalmas-Katz's comments. EPA estimates lifetime exposures to 1,4-dioxane from various sources, assuming that these exposures from the environment are roughly 33 years based on EPA's Exposure Factors Handbook. The Exposure Factors Handbook uses one citation to justify its claim of 33 years of residential occupancy, which is a study from 1992 using data from 1987. This study doesn't represent the best available science as its data set is overly narrow and decades old. There are also several methodological limitations identified in the study that impact its generalizability and applicability, including limiting the study population to homeowners, failing to consider racial or economic demographics, and using a Monte Carlo methodology that underestimates the occurrence of very large occupancy periods or highly exposed populations. Together, these limitations make the study inappropriate to inform calculations in the draft supplement, as it will severely underestimate risk. As John said, people with lower social and economic mobility, such as people of color and low wealth people, have historically had higher residential mobility due to lower rates of homeownership, in part because of discriminatory housing practices. In addition, these populations are more likely to move, but they're also more likely to move within the same neighborhoods, meaning their exposures to toxic chemicals would remain consistent despite a change in residence. To effectively account for the duration of residence in fence line communities, EPA must assume a lifetime exposure to air and drinking water of 78 years in alignment with the agency's typical practice. I want to stress that we also do not recommend EPA continue to assume 33 years of residence while waiting for an overhaul of the Exposure Factors Handbook, which would delay necessary protections from 1,4-dioxane, but rather to use a whole life exposure assumption in the short term while waiting for an update. EPA should rely on the best available scientific methods, including probabilistic methods, to quantify cancer risk and exposure estimates that capture real-world risk to strengthen the draft supplement and offer stronger protections for potentially exposed or susceptible subpopulations. In doing so, EPA will additionally meet the agency's goals to address environmental justice concerns in the regulatory and rulemaking process. Thank you.
Thank you. All right, we're getting towards the end, but not quite to the end. Next presenter is Steve Risotto from the American Chemistry Council.
Steve has sent that he will be traveling on the plane during that time. So okay. We will try again in the end if he's back or not.
Okay.
All right.
And then we're not sure about a confirmation from Robert Sussman. Is Robert Sussman with us? Not hearing
right.
him.
He hasn't confirmed, yes.
All right. So then lastly, Paige Varner from the Environmental Defense Fund.
Yes, hi, can you hear me?
Yes.
Okay, great. Good afternoon. I am Dr. Paige Varner, and I'm a scientist at Environmental Defense Fund. We commend EPA for its improved supplemental analysis of 1,4-dioxane. However, we have major concerns about the supplement and the included fence line assessment methodology as it relates to charge question 4. As EPA notes, this draft supplement is the first risk evaluation conducted under TSCA since EPA acknowledged the need to assess fence line community risks. As this assessment will likely be a model for future risk evaluations, it's critical that EPA adopts a scientifically sound fence line risk assessment methodology that accounts for real-world aggregate and cumulative risks. However, the current piecemeal approach systematically fails to account for these real-world aggregate exposures, and in doing so, underestimates the increased risk to communities from 1,4-dioxane. I would like to highlight these specific shortcomings while noting that we have also provided written comments submitted to the SAC. First, EPA has failed to consider risk to people who are exposed to 1,4-dioxane from multiple routes of exposure. EPA claimed not to aggregate across exposure routes due to the uncertainty around the extent to which cancer risks across routes are additive for 1,4-dioxane, among other uncertainties. However, aggregating exposures from multiple routes actually reduces uncertainty by providing exposure estimates that more closely reflect real-world exposures. Specifically for 1,4-dioxane, due to the linear no-threshold model of 1,4-dioxane's carcinogenicity, multiple exposures, regardless of the route of exposure, are assumed to be additive. If there was indication of different tumor sites for various exposure routes, risk estimates themselves across tumor sites and exposure routes can be aggregated. Therefore, EPA does not provide a compelling argument for failing to aggregate inhalation, oral, and dermal cancer risks and must do so. Further, EPA has failed to aggregate exposures from multiple conditions of use. This fails to consider the risk to fence line communities and workers who live in those communities from one or multiple facilities that operate under multiple conditions of use, and therefore has further underestimated real-world risks. Additionally, EPA dismissed fence line aggregate risks in its multiple facility analysis. EPA concluded that aggregate analysis did not identify locations where cancer risk greater than benchmarks that did not already have cancer risk above that level from an individual facility. The point of assessing aggregate exposures, however, is not merely to identify whether a particular community is above or below the cancer risk benchmark, but rather to determine the full extent of the risk to the communities that are exposed to 1,4-dioxane from multiple sources. EPA must therefore calculate and report the true combined risks from exposure to 1,4-dioxane from multiple neighboring facilities. Next, EPA has failed to consider the cumulative risk to communities exposed to 1,4-dioxane and other carcinogens. Residents of fence line communities are cumulatively exposed to multiple chemicals at the same time, rather than experiencing exposures in isolation. As is the case with 1,4-dioxane and other carcinogens, exposure to multiple substances that cause the same negative health effect increases their susceptibility to harm. Failing to account for these chemical co-exposures underestimates their risks. And lastly, EPA has used non-conservative models in calculating risk to fence line communities through the ambient air pathway. In its ambient air screening methodology, EPA used its indoor/outdoor air calculator to estimate exposures. However, this model cannot predict emissions within 100 meters of a facility. EPA should not use a screening methodology, especially for the aggregate analysis, but rather use the full detailed fence line assessment with the air mod model to estimate fence line exposures. Data input into this model should be the highest reasonably foreseeable releases from a facility within a multi-year period, rather than using a single year of data, such as in this draft supplement. In conclusion, these specific areas in which EPA has underestimated risk to workers and especially to fence line communities are not in line with TSCA's mandates of using the best available science and assessing exposures to potentially exposed and susceptible subpopulations. EPA has systematically taken an approach to determine whether an individual condition of use within individual exposure routes for one chemical contributes to unreasonable risk. This piecemeal approach underestimates the magnitude and type of unreasonable risk presented by 1,4-dioxane, which is not consistent with the whole chemical approach that EPA claims to take. This leaves unreasonable risks unaddressed that, if not addressed, will ultimately influence risk management decisions and continue to leave populations at risk from 1,4-dioxane and other subsequent chemicals that will be assessed and addressed under this methodology. Thank you for your time.
Thank you. Now we circle back to make sure we haven't missed anyone. Is Kate Jacobus with us or comment? All right. How about Steve Risotto? Did he make it on? And then finally, Robert Sussman. So with those folks not having showed up, we're done with the public comments. I'll open it up to the committee for questions to the presenters. So are there questions that any of us have for the presenters? I see Dr. Barakal.
Yes, this is Dr. Barakal. I wanted to ask a question. I heard several of the public presenters that mentioned reference to the fact that the exposure to the cleaners was the EPA was using was not correct. And I wanted to know whether there are data sources that they could refer to. I'm sorry if you have mentioned this in your public written comments. I didn't have the chance to go over them, but I just wanted to know whether these are there are actually databases that could be used to effectively and more accurately represent the variability in the population in terms of exposure to dish soaps and other cleaners, or this is more like, notion that unfortunately there is not actual data that could be leveraged. So I think this goes to Jonathan Kalmus-Katz, but I think also another person mentioned that.
This is Paul DeLay with American Chemistry Council. Just mentioning it, with respect to concentration of 1,4-dioxane in formulated products, that goes to the source I mentioned was a database maintained by the New York State Department of Environmental Conservation that based on their restriction of the level of concentration permitted in products sold in New York, which is going to be similar to products sold throughout the country. The limit is 2 parts per million in this year, and it's going down by the end of the year to 1 part per million. And they allow companies to request a waiver for 1 year, and there's a database of those products that have received a waiver. And again, those products generally have concentrations from about 2 to 15 parts per million. So you have at least in terms of concentration formulated products, there are sources that are very current.
Yes, I actually was asking more about the time, because I think in the SHADS HT model, there are databases that are used, activity diaries that basically give an idea of what an individual is, a random individual from the population is the time that the person is exposed to an agent. And so I wanted to know whether there were databases that report time, since I think Jonathan had mentioned specifically that aspect, or I don't know if I misunderstood your comment, Jonathan.
No, you did not misunderstand it. I think that's right. I think what we have here is EPA taking the same exposure durations for these products that it used in its prior supplement, which was intended to evaluate consumer use, and applying them to workers. So you have these kind of 20 to 30 minute kind of exposure durations for dish soap, for kind of surface cleaners, and whether or not those are kind of correct with respect to consumers, they're clearly understating occupational risk. We have some kind of information about kind of refuting kind of the numbers that EPA has relied on in our written comments. I'm not aware of data sources that provide kind of specific information, except there is information about the length of work shifts, which can be used kind of as a proxy, like basically, and we do provide that. There's kind of, the Bureau of Labor Statistics has some of that information. We cite some of that in our comments. Like generally, if a dishwasher is working an 8-hour shift, and we provide some information about the length of the shift, and similar for custodians and for janitors, I mean, given the nature of their job, I think it is a reasonable assumption that they are exposed for kind of the vast majority of that time period. So I think that in the absence of data, we would suggest for many of these kind of products, you can use the length of the work shift as kind of a reasonable proxy.
Thank you. I just would like to offer, this is James Kim from American Cleaning Institute, that if we're talking about occupational exposures in a formulation plant, that's where there is data that's limited, and we have offered to EPA to work with them to try to obtain more accurate, more recent information on that.
Thank you. So Dr. Ottinger, you have a question?
Yes, just a quick question. I believe Dr. Azam, I'm sorry, I'm mispronouncing your name.
Hi, it's Rias. I'm also not a doctor, but thank you for that though.
It just was curious about the WHO method and how it worked. You suggested 78 years. And I wondered if that was like a, one number for each year that you just simply add together, or how exactly that works. I can't hear you. I'm sorry.
Of course. So the WHO methodology and the 78 years number are of 2 separate points. So 78 years is EPA's kind of whole life exposure number that they use. So when when we're hoping that we're right now, what EPA is doing is it's assuming that you change your address at 33 years alone, and after that, your exposure ends after that 33-year segment. We know that that's not necessarily true. We especially know that that's not true of communities that EPA is supposed to be prioritizing and is explicitly told to prioritize under TSCA. And so, and in our technical public comments, we actually have some research cited around the proportion of low-income folks as well as brown and black folks who actually stay within 100 miles of where they were raised, which is some number like 80% or something like that, if I remember correctly. So that 78 number is more, EPA has a typical agency practice around just a lifetime is 78. So we're just hoping that they use that and apply it over here because the Johnson and Capel study, which is the exposure factors handbook citation, is not the recommended. We would not recommend it as the best available science. Under the WHO methodology, I think there's people on this call who are probably more suited to illuminate that for you. I'm looking at you, Dr. Heiger-Bernays. But this is a methodology used by World Health Organization, recommended by the National Academies. UCSF published a manuscript paper back in January outlining probabilistic dose response assessment. We've published a number of technical appendices, including one for the 1,4-dioxane supplement, outlining this method in comparison to the method that EPA uses and showing that the MOE approach severely underestimates risk to everybody on non-cancer health, and especially for risk management, it's important because it doesn't provide a number. And so if you do not have a number, you do not have a benefit. And if you don't have a benefit, then you do not have a protection.
Understood. Okay, thank you very much.
All right. So Mike Wright, Mr. Wright, do you have a question?
Yes, I do. This is for Dr. Kim. And I wondered if the ACI has any data regarding the occupational use of your consumer products, which contain 1,4-dioxane. For example, people who will be janitors, for example, or people who do domestic cleaning. Are there any data at all about their exposure?
So I think what we've recommended in our comments is that EPA, when they model those types of exposures, that they use the maximum allowable concentration limits in those products that the New York DEC requires. And that is because most of the products adhere to that maximum allowable concentration. We also noted that there is a waiver system at New York, and so that information is available. And so you can see what the concentration are of the products that were waived from that requirement for this upcoming year. And if you use those numbers, I think you get a conservative estimate of what the exposures could potentially be.
But you don't have any direct exposure data. Thank you.
All right, so do I see any other questions? Okay, we have about 45 minutes left in our day, and we have a decision whether to start a first question or not. I think by the time we get the question read into the record and start working on it, we'll probably go overtime. I'd like to ask Dr. Portier what he thinks about that. Are you folks in such concurrence with the first question that you think we can get done with this in 45 minutes, question 1A, or maybe just wait till tomorrow?
Well, Dr. Cobb, I have a lot of comments on 1A already written. I'm in the process of consolidating it down, so tomorrow's presentation would be more concise than doing it now. I mean, we could move now, but like you said, we'd probably go over because I have probably myself with the summary that I have is about 40 minutes.
Yeah, that is even though it's a short word there are not very many words in that question. There's a lot there. So I kind of figured it would be a long response. So I think that we should adjourn for the day and start back at 10 a.m. Eastern time tomorrow. And for the panel members, if you think of things over the evening that we need to redress first thing in the morning, if the agency has responses to any of our questions, we will start with those and then move directly into charge question 1A.
Well, thank you, everyone. And the meeting today is adjourned. Thank you.
Thanks, everyone. Hey, Allah, are you still there?
Yes. Let's make sure that the recording is off. Will, can you turn off the recording?
It's what I wanted to talk about. It's okay.
Yes, 1 second.
So towards the end there, maybe the last